So for this reason, there has been a continuous interest in approaches aimed at improving the magnetic properties of nanoparticles by means of the control of the surface structure. So the surface is characterized by breaking of lattice symmetry and disorder due to the random missing atoms making incomplete the atomic coordination sphere. The effects of such features on the magnetic properties are increase of particle anisotropy due to the contribution of the surface anisotropy, determining surface spin pinning, and the decrease of particle saturation magnetization because the spin disorders make the surface magnetically inactive. This represents a great limit for those applications of nanoparticles requiring high moments, like in biomedicine, where the particles are magnetically driven toward the tumor cells. Thus, to make the surface magnetically active, contributing to the magnetization of the particle, is a great challenge. So in order to achieve such an objective, an approach which proved to be very effective is the exploitation of the interaction between the surface of the particle and an organic molecule that is realizing an organic coating. And the role of the coating is in improving the magnetic properties of the particles, introducing a modification of the surface aimed at decreasing the surface structural disorder. The effects are increase of particle saturation magnetization and decrease of particle anisotropy. As reported in this plot, for instance, for 4 nanometers manganese ferrite particles coated by benzoic acid, the coated particle shows a saturation magnetization larger and a coercive field smaller with respect to the native particles. But how such decrease of the order is produced? So the action of a proper molecule is aimed at decreasing the order, but aiming at reproducing the bulk-like crystal environment around the surface atoms. And the effect is achieved through specific coordinated functional groups which bind to the surface atoms. They take the position of the missing atoms. They replace the missing bonds and the occupancy of the d orbitals of the surface atoms, and actually they restore the atomic coordination sphere and the interatomic distances of the bulk atoms. As a consequence, the surface magnetization increases because, due to the reduction of anisotropy, the pinned spins are no longer pinned. They become free of being aligned along the magnetization of the core, along the direction of the magnetic field. A very good example is reported in these 2 papers. So it was obtained an increase of the saturation magnetization till to 80% of the bulk value at room temperature in magnetite 5 nanometer particles by a coating with oleic acid. And differential field theory, okay, the density, the DFT calculation, and the detailed STEM ELS experiments provide an evidence of the order produced by the coating, and specifically of the bonds between the oxygen of the carboxylic group of the oleic acid and the iron atoms, completing the first atomic coordination sphere according to the tetrahedral and octahedral symmetry of the spinel lattice. In this paper, the authors focused their attention to the reduction of the anisotropy. And in this table, it is reported the percentage decrease of the coercive field for a series of benzoic acids on the coercivity of 4 nanometers manganese ferrite particles. They differ in the functional group, you see R. And with increasing the pKa, the percentage of decrease increases, reaching 48% for the functional group OH. The pKa is a measure of the strength of the acidity, and the Ka is a constant of dissociation of an acid. So higher is the pKa and weaker is the acid. The acid is an electron acceptor. Then the increase, if the acid becomes weaker, it means that the R substituent is more electron donating. And as the donating character increases, electron donating increases, the crystal field splitting energy increases, and the spin orbit coupling, the main responsible for the surface anisotropy, decreases, and then the coercive field decreases. So this paper demonstrates how is important the knowledge of the surface coordination chemistry in order to understand the mechanism for modifying the surface structure. In this example, it is shown the size-dependent decrease of the coercive field in a series of organic molecules coating the surface. With increasing the particle size from 4 nanometers till to 25 nanometers, you see that for each acid, the percentage of decrease becomes smaller and smaller. Okay, this was expected, and it is a demonstration that with increasing the particle size, the role of the surface becomes smaller and smaller. Now I'm going to present the results of a work of our CNR group in Rome in collaboration with the Democritos group in Athens. So we compared the effect produced by 2 different organic molecules on the magnetic properties of 5 nanometers cobalt ferrite particles. The organic molecules are the ethylene glycol, where the functional group is the hydroxylic OH group. In this case, the interaction is electrostatic, then it is weak. And the oleic acid, OA, where the functional group is the carboxylic one, COOH. The bond is covalent, then it is stronger. So the presence of the adsorbate molecules and of the bonds established between the functional groups and the surface atoms are shown and evidenced by differential thermal analysis through the weight loss exothermic peaks associated to the decomposition of a monolayer of the organics coating, and by Fourier transform IR spectra show through the shift of the characteristic stretching signal vibration of the different functional groups for the two organic molecules. Mossbauer spectra were performed at 12K, applying a field of 8 Tesla. The fitting to the 2/6 corresponding to iron in tetrahedral and octahedral sides of the spinel lattice allowed us to detect a ferrimagnetic canted structure and to determine the distribution of the atoms between the two lattices. You see there is a difference, and such a difference is due to a different structure, atom distributions on the surface. And below you see the fitted parameters of different type. So hysteresis cycles show for the DEG coated sample a lower coercive field, larger saturation magnetization. This demonstrates that for the DEG coating, the effect of reducing the surface order is higher. So it is more effective in this regard. Magnetization measurement as a function of temperature show a maximum. It is related to the average blocking temperature, which is determined by effective anisotropy. They give an evidence of strong interparticle interactions as shown by the flattening of the magnetization curve, field-cooled equilibrium magnetization curves at low temperature. And these interactions, so strong, are confirmed by the so-called delta M versus H plots. Delta M is the difference, is given by this equation where the two different remanent magnetization are reported. So such plots provide an evidence of the most important predominant interparticle interaction between dipolar and exchange. The negative deviation from the baseline indicates predominance of dipolar interactions, and you see the deviation is larger for the DEG sample. So in this sample, the interactions are much stronger. They are stronger because of the larger moments, the saturation magnetization is higher, and also because the intercore distance is shorter, since the thickness of a coating monolayer of DEG, 0.8 nanometers, is smaller than that of the OA coated sample, 2 nanometers. So in this case, DEG coated sample, the moments of the core are closer. I move now to the physical modeling by the Democritus group. It was based on electronic structure calculations, developing an atomic scale model, Monte Carlo simulations using a mesoscopic modeling of nanoparticle assemblies. So the two investigations, the two types of calculations are complementary, and the Monte Carlo simulations used the values of the magnetic parameters calculated by the FT. So the magnetic moments, the anisotropy energy, and the exchange constants were calculated for a particle of 2 nanometer size using the cationic distribution obtained by Mossbauer spectroscopy. And the relaxed structure were also calculated. The table shows for the two coated sample and for the cobalt ferrite bulk as a reference, the values of the mean atomic moments of iron and cobalt, and the value of the magnetocrystalline anisotropy. You see that for the DEG-coated sample, the moments are larger, especially for cobalt, and the magnetocrystalline anisotropy is smaller than that for the OA sample. So the value for the DEG-coated sample are closer to those of cobalt ferrite bulk. And this is a confirmation that such a coding is more effective in reducing the surface disorder. The observed differences are due to different cationic distributions and different spatial distortion of the surface configuration induced by the organic molecules. In the OA-coated sample, the covalent bond is stronger than the simple electrostatic bond, and it leads to a more distorted structure and then produces a bigger reduction of the d orbital moment. The cobalt moment is more affected by the distortion because cobalt is predominantly in octahedral sites, and in such symmetry, it has a high orbital moment. In the crystal field theory, the fundamental energy term for cobalt in octahedral site is T term with a high orbital contribution. I move now to Monte Carlo simulations. It is based on a mesoscopic modeling of a random assembly of interacting ferrimagnetic core shell particles. The originality of the model is the use of 3 spins for describing the properties of a single particle. 3 spins instead of 1 microspin like in this classical Stoner-Wolford method. So 1 spin is S1 for the core, and 2 spins, S2, S3, are in the surface shell for the opposite, indicating the opposite direction. S2, S3 on the surface are exchange coupled between them, and each of them is exchange coupled with the core moment. So the system considers an identical spherical ferrimagnetic core shell particle located randomly on the nodes of a simple cubic lattice. Each moment has a uniaxial anisotropy axis randomly oriented. Both intraparticle and interparticle features interaction are taken into account, and the moments, the anisotropy constants, and the exchange coupling constants were taken from DFT calculations. These 2 tables show the values obtained from DFT calculation, rescaled to the particle size of 5 nanometers, because DFT calculations were performed for a particle size of 2 nanometers, of the magnetic moments and the effective anisotropy constant. Of course, magnetic moment of the core is unaffected, and the magnetic moments for the DEG-coated sample are larger than for the OA-coated sample, and this results in the experiment in a larger saturation magnetization. The anisotropy constant for the diethylene glycol sample, coated sample, is smaller than that of the OA-coated sample. This results in the experiment in a lower coercive field, providing further confirmation that the decrease of order in the surface structure is better, is higher in the DEG-coated sample. So this is the Hamiltonian that was used. The energy terms are intra-particle exchange interactions. You see the different exchange coupling term. The core anisotropy energy, the surface anisotropy energy with the corresponding anisotropy constant for the core from the surface, the Zeeman energy, the dipolar interaction energy, and finally the interparticle exchange interaction energy for those particles which are in contact. Below, the magnetic parameters are reported, obtained from DFT calculation, the exchange integral, the anisotropy constant, and the magnetic moment. So here there is the comparison of the experimental curves and the simulated curves. Monte Carlo simulation show a very good agreement with the experimental finding. They are able to reproduce well the behavior of the different curves, magnetization versus temperature, delta M plots, and hysteresis cycles. So, come to the conclusions. The results I showed you give a demonstration that a proper organic coating is an efficient tool for tuning the magnetic properties of nanoparticles by reducing the surface disorder. The magnitude of the effects on the magnetic properties depends closely on the type of coordinating functional group bound to the surface, its capability to restore the atomic coordination sphere of the bulk atom, the type of bonding, the type and degree of distortion produced by the organic molecule. In order to optimize such properties for obtaining and improving of the magnetic properties requires a deep knowledge of the surface coordination chemistry for understanding the basic mechanism. Final message, a proper organic coating can be used to optimize the magnetic properties of different nanomaterials, not only nanoparticles, also thin films, for a variety of applications where the surface plays a dominant role, not only in biomedicine, but also in spintronics. But I would say in every type of application where a dead surface layer is unwanted. Thank you for your attention.
Okay, let's turn on our microphones, and cheers, Professor Fiorani.
Thank you.
Okay, let's move on to the next talk, which will be given by Professor Manuel Vasquez. Manuel Vasquez is head of the group Nanomagnetism and Magnetization Process, Institute of Ciencia de Materiales de Madrid. And Manuel works with domain structure and domain wall motion in cylindrical nanoiris and glass-coated iron cobalt-based microiris. And he develops magnet sensors, magnet nanoiron arrays for application. And the title of his talk is Magnetism of Cylindrical Nanoiris. Please, Manuel.
Will you please close the microphone, please?
Can you hear me?
Yes, Manuel.
Yeah, but I think there's something.
Belita, please, can you turn off your microphone?
Yeah. Oh, I found it. Okay. I didn't know what it was. Okay.
Okay, thank you. Dino? Can you please turn off your microphone?
Okay. Okay, just.
Thank you. Okay, Manuel.
I'm trying to get connected with to share my screen. Okay. Can you see that?
Not okay. It's coming. Yes.
Moment. I'm trying to. No, okay.
Great.
Now
Great, Manuel.
it is all right. Okay. Well, first of all, thank you for the invitation. I'm very pleased to be here today to be with you, with Sergio, Professor Sergio Rezende, and all our friends in Recife. Well, I'm going to talk about cylindrical magnetic nanowires. I will try to summarize some of our last works in Madrid. And I have to say always cylindrical nanowires, because most of the times, or many people are working in nanowires, but actually they are nanostripes. So our wires are cylindrical properly. Okay, but before going to the nanowires, I would like, if you allow me, 2 minutes. It is my pleasure to join, as I mentioned, to join this meeting and to celebrate the Sergio Rezende. So it is clear to me, and I think many people knows about the outstanding contribution of Professor Rezende to the Brazilian society in many respects, but particularly in science and technology, he's so well known, and particularly even more in particular in magnetism. He has done a lot of contribution in fundamental magnetism, and this has been performed in a way sharing his very high responsibilities in politics and administration. And in fact, well, this picture is when I met Sergio in Recife 8 years ago. He was showing the downtown Recife. He was very happy, and I was very happy also that he was able to show me Recife. But I know the people from the University of Pernambuco in Recife. I follow the work from the middle of the 90s with the discovery of the giant magnetic impedance. I remember very well the very early work by his group, and particularly by Fernando Machado. He did a very good job. But then, of course, I was in Recife when Sergio organized the ICM. It was fantastic. But also I have met in other conferences. For example, I remember in the ICM conference in Karlsruhe, and the IUPAP meeting in Rio. Was a member of the commission in this IUPAP, was in 2012. And then the last visit to Recife was 1 year ago, supported by the CAPES, the Brazilian CAPES. Was also very nice to stay. Well, after that, I'm going to continue with the nanowires. You know, the curved nanosystems are becoming more and more interesting because they introduce some new effects in physics, and the new materials having this curved structure, they offer new possibilities as a material and for physics. I can mention, for example, you see in this image the nanowire, nanotubes, vertical solitons for theory, so thin films with curvature or kind of helix, and so on. And the particularities of the cylindrical nanowires are based in this cylindrical geometry. They are related to some new topological effects, and also it is possible to tailor that diameter of these nanowires, and it's possible to have some modulations in composition. In my presentation today, I'm going to summarize our work on nanowires, as I mentioned before, particularly paying attention on the magnetic domains and the reversal processes in modulated cylindrical nanowires. Okay, what type of nanowires are we talking about? So in our laboratories, we prepare these nanowires inside templates, porous templates, and we can tailor the diameter in the range from 20 to 200 nanometers, roughly, and the length between 1 or 200 nanometers until 40, 50 microns. So we can have a very large aspect ratio. And they can be prepared in a out of plane of the porous membrane, as you see in this same image, but also, in a cylindrical, a radial nanowires, starting with a cylindrical template. But as I mentioned today, I'm going to talk about modulated nanowires, modulated in composition, for example, multi-segmented or multi-layer, as you can see in this image here or here, having radial compositional modulations, for example, nanotubes or core cell nanowires, and also with modulations in diameter. You see here a couple of examples. This cobalt iron nanowire with modulation in diameter, and this also with modulations in diameter, but also in the composition. I will pay attention today only to individual nanowires, I mean, after release from the membranes. Well, as I mentioned, there is a number of applications where these type of nanowires and the arrays can be applied. They are studied currently in 3D magnetic structures and logic gates, or even for neuromorphic computer. Well, I don't have time to explain in more detail, but some other applications can go from information storage, for example, well, this is for the arrays of nanowires, for spintronic devices for sensing the magnetic field, or microwave electronics, or for example, in biotechnologies. Here you see an image of osteosarcoma cell eating some segmented nanowires, or also these nanoswimmers, kind of hybrid magnetic nanoeels with a magnetic head and a non-magnetic tail, or also multi-segmented wires for security barcodes. Well, the cylindrical geometry introduces some particularities, as I mentioned. If we pay attention only to the shape, depending on the ratio between the length and the diameter, we can have different ground states, magnetic states. If we have a wire which is very long, we have the easy axis is longitudinal, is axial. We will have a single axial domain. If in this particular region here, like an aspirin, do we have the easy axis is a transverse direction, or in this other big region, we have a magnetic vortex. The vortex, as you see here, we have essentially an azimuthal or circumferential magnetic moments, but at the very end, where we have because of a exchange coupling, we have a singularity. And in general, this curvature induces non-trivial topological phenomena. For example, we can see helix or block point domain walls, or even ischemion tubes. We are working now on that. We are, for the moment, we are in the more the simulation aspects, but also some other magnetochiral systems are determined by the curvature of the nanowires. And a particularly interesting aspect is the presence of the type of domain walls that appear in these cylindrical nanowires. For example, we can have transverse domains, like this is schematically viewed here. This is similar to the nanostripes, but we can have also so-called block point domain walls. In the very axis of the wire, we have a mathematical singularity. well, we don't have time to go into detail, but it determines the magnetization process in very fast domain wall motion. But on the other hand, we pay attention to the crystalline structure. We are not working with permalloy, where we can forget about the magnetoelastic or magnetocrystalline anisotropy, but we are working with cobalt-based nanowires. And the magnetocrystalline storage anisotropy is very important. For example, we see here an iron cobalt nanorod nanowire with this a single crystal FCC cubic. This cubic symmetry introduces a relatively small magnetocrystalline anisotropy, particularly compared with the shape anisotropy of these nanowires. And here in this other case, we got a cobalt nanowire having it's a single crystal with HCP symmetry. This HCP symmetry introduces a very strong magnetocrystalline anisotropy. I would like to show a few examples of individual nanowires with no modulations in diameter, so constant diameter. For example, this is for a FCC, a cubic cobalt-35 nickel 65 nanowire. This is a magnetic force microscopy image. You see there are magnetic charges at one end and at the other. We have practically a nearly ideal magnetic dipole. This is the simulations, the magnetization distribution, and we see these distributions, the ends correspond to the magnetic charges observed above. And this is the hysteresis loop measured by magnetoptic Kerr effect of this nanowire. We see a single Barkhausen jump. We have a kind of bistable nanowire with a large jump produced by the reversal of magnetization along the axis. In other cases, as I'm showing you here, we can observe transverse and vortex domains in other cobalt nickel alloy nanowires. It can be possible to do with PIM, photoelectron emission microscopy with circular dichroism analysis. In this case, and due to the curvature, favored by the curvature of the nanowires, it is possible to get information not only of the magnetic distribution at the surface of the nanowire, but also in transmission. We can get information of the orientation of magnetic moments inside the nanowire. And for example, this is for two alloys, cobalt 85 and cobalt 65. In the case of cobalt 65, we observe, well, some regions with F cubic or hexagonal symmetry. And if we focus in these particular regions, the red one and the blue one, the red one, it actually corresponds to a very clear interpretation of these images. We have clearly a vortex, a single vortex domain. While here to the left, we observe here, we have a clearly multi-transverse domain structure. This part here, what is mentioned, the shadow, correspond to the internal part of the nanowire. And also, we can observe this type of very complex domain structure by electron holography. So this is a cobalt nickel single nanowire. This, I would like to pay attention first to this image in the middle, where we have some local regions with FCC cubic symmetry and some others with HCP, with hexagonal. And this is the electron holography image, where we can see, particularly when we have, when we have this region of HCP symmetry, we have a kind of vortex which are perpendicular to the axial direction of the nanowire. And these vortices are separated by kind of by transverse domains, which are marked by arrows. And this very exotic domain structure is determined by the minimization of the local energy from a crystalline point of view and shape anisotropy. Okay, let's go to the modulated nanowires. First, I will mention a couple of examples with modulated in diameter. You see here couple of images. To the left are different segments of nanowires with the same composition but different diameter. And this is kind of anti-notched nanowires with modulation, very local modulation in the diameter, with larger diameter, as you can see in this same image. Well, electron holography again give us very nice images of the magnetic field distribution. This is a combination of SEM and electron holography images. You can see this color represents the lines of the magnetic field. They go from a transition of diameter to the other local region. So it indicates that we have some accumulation of magnetic charges just where the transition of diameter take place. Or the opposite we have here, well, in the other part with a large segment. Similarly, what you can see here, this is the same image of a wire with a number of modulations in the diameter, and here you see the similar image for a number of multi-segments. Well, we performed some magnetoptic current effect measurements in this type of nanowires with the same composition but different modulation in diameter. Is iron cobalt, BCC, or no, sorry, FCC cubic. And this is the hysteresis loop for a wire without modulation. We have very clearly a single Barkhausen jump. It is a bistable loop. Then working with different wires, with different type of modulations, we can observe that in some particular cases, we have a number of jumps, Barkhausen jumps in the magnetization reversal. We can ascribe this a number of jumps to the pinning of the domain wall in the different positions where there is a change in the diameter. Well, we have studied these diameter modulated nanowires with micromagnetic simulations, MUMAX simulations, and you can see here to the left that depending on the diameter, I don't know why I'm touching, move the slide, sorry. These are the simulations, and we can reproduce the hysteresis loops that we observe in these nanowires. Well, of course, not completely, but well, at least very, very significantly, well, qualitatively. What is very interesting is that from these simulations, we have introduced a kind of pinning that we have labeled corkscrew because of the shape of the screw. In fact, this screw in the segment with the larger diameter, it means that the axis of the core forms a kind of helix. So it's not at the very center of the wire, of the nanowire, but making a helical displacement along the segment. Let's go to more rapidly to these bamboo-like modulations in this type of nanowire. Well, this is a bit complicated to explain in 1 minute, something like that. This is a variable field magnetic force microscopy imaging in uniform to the left compared to modulated nanowires like that. You see here a scheme of this nanowire, modulated and the homogeneous diameter. So applying a different magnetic field, here large field, we observe white and dark regions where we have accumulation of magnetic charges. And when we change the field, we observe that these charges get into the nanowire. And from that, it is possible to, well, following with the series of the applied field, we can reconstruct the hysteresis loop in the local regions. For example, this square loop in green correspond to the homogeneous nanowire near the end of the wire. If we go to the modulated nanowire, we observe a similar effect, but even for the largest field, we can identify the position of these modulations in the emitter. And what is more interesting is that the reversal process takes place before getting a large displacement of a domain wall. So the wall remains blocked in some local regions where we have these modulations. In fact, you see here down the hysteresis loop, which is reconstructed in the case of this modulated nanowire. It is not perfectly symmetrical, as I would expect, because it's not, well, we have some local inhomogeneities in one end and the other. Well, let me go, I think already 20 minutes. I will complete this presentation with some examples of modulated nanowires modulated in composition. We have considered two types of modulations. One is considering ferromagnetic modulations, like here to the left. The final objective is to get a modulation in anisotropy. And in fact, there we can observe transverse, vortex, and axial domains. And the second case is when we have a multi-segmented nanowires with ferromagnetic and non-magnetic segments, like the one here to the right. Well, for the multi-segmented ferromagnetic, I would like to show you a few examples of cobalt 85, nickel 15 for the magnetic segment, and nickel for the for the different segments, also magnetic, but with different magnetic anisotropy. Cobalt 85, nickel 15 is hexagonal, and nickel is FCC. So this is the topography image, and this is the magnetic image down. So you see the nickel segments are always axially magnetized, is in yellow, while the cobalt nickel segments, sometimes we have here two vortices. Here is only one, this one, and a small one. So we can have a number of multi-vortex structure. And particularly, we have observed that depending on the length of the cobalt nickel segments, we observe different domain structure. For example, we keep constant nickel length segment at around 800, while for cobalt nickel, we have 600 nanometers. In this case, we have single vortex domains for the cobalt nickel. But if we increase to 1,200 nanometers, we have double vortex domains. Even more, if we have a larger segments of cobalt nickel, up to, for example, 1,500, we can observe multi-transverse or multi-vortex domain structures. This is a consequence of the interactions between the nickel segments and we are doing just currently some simulation to interpret, to unveil this the phenomenon by which we can obtain different domain structures. And the last example I wanted to show you is a multi-segmented ferromagnetic and metal multi-segmented nanowire, but with the particularity that at one end we have short length domains of iron cobalt. At one end you see 260 nanometers, and at the other end we go 560 nanometers. So we increase continuously the length of the segments, of the ferromagnetic segments. Here, some magnetic force microscopy image that, interestingly, we have confirmed that when we apply the reverse field, the propagation of the domain wall along the nanowire starts always at the end, having the shortest segments of cobalt nickel, of iron cobalt nanowire segments. And we have a number of experiments, and we observe always that the propagation for positive or negative field always starts in the short segments. This is even more nicely observed in these beam images. So you see to the left of, we start from a negative saturation in white under minus 700 Ørsted. Then we reverse the field, and we observe that as we increase the value of the black field, the domain, the reverse domains goes from the end having the shortest length. And the same happens when we start from the opposite saturation state. Well, in fact, we have observed this way what we are calling a magnetization ratchet. So the propagation of the domain wall starts always in one direction. This, this is a consequence of magnetostatic interactions between the nanowire, the segments inside the nanowire. Well, I think I'm finished. This is the last slide. As a summary, again, thank you very much. This is my pleasure to join you here in this celebration for Professor Sergio Rezende. If you have some questions, you can tell me or later, as you like. Thank you very much.
Thank you, Manuel. Let's turn on our microphone to say cheers to Manuel. Okay, let's move on to the next talk, which will be given by Professor Burkhard Hillebrands.
Yeah.
Hillebrands is professor of experimental physics at the University of Kaiserslautern. He works with many things, but his special interest is in spin dynamics and fundamental properties and applications of spin waves. He is also interested in material properties of magnetic fields and nanostructures. Professor Hillebrandt is going to talk about Bose-Einstein condensation of magnons in confined system. Thanks, Burkhard.
Yeah, thank you. Can you see my screen? Does it work?
Yes, that's great.
Okay, so first of all, thank you very, very much for inviting me to this very honorable symposium on the occasion of the 80th birthday of you, Sergio. I must really begin with a big thank you for all the interactions we had over the years. And the interaction was twofold. It was on a very pleasant personal level, and it was also on the science level. And you see a few examples. The very first example we heard already, you started your career with parametric pumping, and I will talk a little bit about parametric pumping. Very important was your contribution about the theory of the Bose-Einstein condensation. And I don't know whether the entire audience knows, Sergio has written this part while you were Minister for Research and Technology, where normally people think you have been extremely busy. So it's really very admirable that you had the time to do this kind of theory. And it was over all the years, the right stuff spin damping in ultra-thin magnetic films. This is nearly 20 years ago, very important at that time. And it's a pleasure to edit this volume. And I was very thankful that you agreed to do this. So a big thank you. And what I should also say, happy birthday, Sergio. And I hope you still have a couple of very good years to come to work, to continue your work in science. So today I would like to talk about Bose-Einstein condensation of magnons in confined systems. So what is new? Of course, we have to go into new dimensions. You have seen the fundamental theory Sergio did some couple of years ago. So I would like to go into very small structures, so where you really have confined spin waves, and I will show you what is going on there. And actually, we can, due to the confinement, we can learn a lot of different things. But let's just get started. We will start with something which we like to call a magnon gas. So that is a gas of magnons, the elementary quanta of the spin waves. You see here a very nice simulation of what it looks like. If you would like to know more about it, what you have to do, you have to grab the right books. Fortunately, these books are around. For instance, I found this book here, where there is all the fundamentals of magnonics written down. Let me just summarize what we need now for my presentation. Essentially, what we need is magnons being the quantum mechanical quasi-particles They are the quanta of the spin wave, so they have energy, they have momentum, they have mass. Let me get here my pointer on, then it's much easier. Yes, they have mass just given by the dispersion, the curvature in the dispersion. Of course, they have spin. And magnons have something which is very, very nice. They undergo scattering events, and particularly important is the 4-magnon scattering, the 3-magnon scattering, a couple of other ones. The 4-magnon is very nice. You will see it a little bit later, because such scattering events are particle number conserving, and they are very reminiscent of what you all know about atmospheric physics. There are 2 molecules in the atmosphere just collide, so you have 2 incoming molecules and 2 scattered molecules, in total 4 molecules. So that is the same thing as we find in magnonics, where we have not molecules but magnons, and 4-magnon scattering is very, very important. So let me move on. Why is this not moving on here? It's not going to the next page. Okay. What rules the world is, of course, the thermal distribution. And we have Bose particles here. So the Bose-Einstein distribution matters. And what you see here is simply the magnon density as a function of the frequency omega, and then the number of states matters, and then, of course, the Bose factor. Something all of you know, we have the -1 because for the Bose particles, and what enters is the ratio of the energy, which is h bar omega, over the thermal energy, kT. And what also enters is a chemical potential. Normally, if you discuss atmospheric physics, you do not really consider the chemical potential because the atmosphere is an open system, so it doesn't really matter. But you will see in a second how important this parameter can be. What we can do, we can simply plot this function here. So the quasi-particle density as a function of the frequency, and then we get this blue curve. Actually, what is plotted is a logarithm, but that is only a small detail, both of the particle density and of the frequency. And there is one peculiarity here, and that is a minimum frequency. You will gleich see what that means, because there are no magnonic states below this minimum frequency. So that is a curve. Now we are asking ourselves, how can we achieve Bose-Einstein condensation? You all know Bose-Einstein condensation is that all the states go into the lowest available state. So this Bose state becomes a very, very large occupation number. And if you're looking for a fingerprint, you can already see from this very simple equation here that a very simple fingerprint is given if the minimum frequency h bar omega and the chemical potential become equal, because then the numerator becomes 0, the exponential term becomes unity, but here again, here in the denominator, we have unity minus unity, so this becomes 0. So in other words, the quasi-particle density will diverge, and that is, of course, a very strong fingerprint of Bose-Einstein condensation. So let's take this idea and let's guide our further ideas by this idea, and let's just think a little bit. What you have seen here is a curve you would have at given T and at a given chemical potential, which is assumed to be 0. Of course, what we can do, we can increase the temperature. Oh, sorry, yes, of course, I should mention this. If now the chemical potential becomes equal to the minimum frequency, I just explained it. What happens is now the curve will diverge and we will have an infinite number of particles here in the lowest state. That is what we would expect. Okay, that shall now be the tool what we will discuss. But before I will move on with the physics, let me just say a few words what it might be good for. And of course, we have a very big aim here, and that is that one day we all hope in our community that we will do computing with magnons. So not electrons anymore like with CMOS, or not photons if you want to build a photonic computer, but with magnons. And that is, of course, a very challenging issue. You all know about classical computing. A classical computer is the one where you are just sitting in front of. So we have CMOS, we have electrons, transistors, resistors, and so on. The ultimate game is, of course, the ultimate goal is, of course, very much discussed in the current time, quantum computing. The difference is here we have scalar variables, we have Boolean logic with electrons. quantum computing entanglement becomes very important. And there are a few things actually in between. The optics people have shown us that one can do wave computing with photons, or you actually make wave packets, and therefore some people call it wave packet computing. But there is something in between, and I would like to call it macroscopic quantum state computing. It simply means that instead of single particles, like electrons for your CMOS computer, we now want to use a macroscopic quantum state. And a very, very important person in this field is, of course, Sergio, because he has shown that with Magnons you can do Bose-Einstein condensation, and a Bose-Einstein condensate is a macroscopic quantum state par excellence. So that is what we would like to do. We like to know how much can we use that for computing. Let me say a few more words about it before I go a little bit more into the detail. So the main idea is to find macroscopic magnonic quantum states now, which we can harvest for information transfer and processing. And of course, if we do so, we would like to harvest ideas which exist already in other fields of our field of physics. For instance, to harvest ideas from superconductivity, such as Josephson currents, or superfluidity, like you have in helium-3 and helium-4. And also, if you think about superconductivity, you have transport free of dissipation. So can we have something very similar here? Actually, I have no time to go into this point, but I can just simply tell you there is indeed, in a certain sense, a free way how to transport magnons free of dissipation. This talk I would like to confine, dedicated to Sergio, to macroscopic magnonic quantum states in confined systems, so actually in Magnon waveguides or Magnon conduits, if you like. And why do we name this actually a macroscopic quantum state? Well, you know very well it's a microscopic quantum phenomena. And what you do there, you use a wave-particle duality. So on a microscopic scale, we discuss systems, our quantum systems, and the condition is usually that the length scales are comparable to the de Broglie wavelengths. But if you are able to build larger objects like a superconducting state or a Bose-Einstein condensate, then the nice thing is we can move into the macroscopic world, because now what matters is not anymore the de Broglie wavelengths, but the coherence lengths. And as you might know from the field of superconductivity, the coherence lengths can be fairly large. So we have much larger structures where we can work with. And these are the Bose-Einstein condensates of particles, so the spontaneous population by a large number of Bose particles. And in particular, the BDC of Magnons, what I'm going now to discuss a little bit more. So you see, I try to put here our field into some context. What is also important, that even if we talk about quantum mechanical phenomena, we can put it into a quasi-classical limit, which allows us sometimes to think about this object as classical objects or as quantum mechanical objects. And the quasi-classical limit simply means that we can describe the system by a Gross-Bitaevsky equation, which is very, very nice. Gross-Bitaevsky actually has, in addition to the Schrödinger equation, all the nonlinear interactions in it, which are so essential for this field. So we have the different condensates, and the properties of both types of condensates, whether we do it on a macroscopic or microscopic world, are almost identical, and therefore we can talk about the macroscopic quantum phenomena. And again, we make use of the analogy with numerous other phenomena in Bose-Einstein condensates, such as atoms, supercurrents, Bogoliubov waves, Josephson effects. There are many other of these kind of effects. Okay, now let's go back to Sergio's work. You have seen this figure here. For instance, what we can do, and that is now a research idea we are pursuing here in Kaiserslautern, we just started to work into this field. What happens is if we plot the dispersion of the Magnons or the spin wave as a function of the wave vector, what you see here, it always runs through a minimum. The reason is what you see here in the dispersion is called a backward volume mode. It's called backward volume because with increasing wave vector, you see the frequency goes down. And if you take the group velocity, which is always a slope, you see the group velocity is negative. So in a sense, this mode runs backwards. Therefore, we call it a backward volume mode. And for large wave vectors, exchange interaction kicks in, and then you see a minimum is formed. And this minimum now can be used to have Bose-Einstein condensation. What is so nice about our magnonic systems, we get it always in pairs, namely one at a positive value of the wave vector, and also at the negative value of the wave vector. And now let's jump into quantum computing, because in quantum computing, what you need there is the essential unit is a qubit, a state which is a superposition of two quantum mechanical states. Let's call them plus or minus, or let's call them north pole and south pole, or however you would like to. And the qubit is defined as a phase coherent superposition of these states. So the amplitudes and the phases matter. And what people like to do is to represent such qubits as a state on the surface of the Bloch sphere. So we have the two states here, the north pole state, the south pole state, let's say. And then we look at the superposition, which has a certain amplitude ratio and also the relative phase in between matters, which you see here like phi. And now jumping back to the Bose-Einstein condensates, having two condensates and letting them superimpose, we have a perfect representation of a quantum mechanical qubit state in our magnonics world. And I think that can open many, many things. One little secret behind, normally you have to go to very, very low temperature in order to achieve that. You know, if you want to build a modern quantum computer, you have to have a very, very large and very, very efficient fridge, because everything works at very low temperatures. You do not want to disturb the system with thermal energies. That is very different in our magnonics world. We can work at room temperature. And the reason is simply that we have this minimum frequency here, which helps us to separate the state well enough so that room temperature will work. Okay. Bose-Einstein condensation has been studied since many years, since about 15, 20 years now. And it was made possible by a process which Sergio started already to discuss at the very beginning of his career, that is parametric pumping. And here is a very effective way how to do this. You see again the dispersion you have seen in Sergio's graph. Here it is shown again in blue. There are many other states around. They actually form even a continuum of states. And now what we can do, we can use parametric pumping. So we take a microwave photon, and it splits in this representation into two magnons at half the energy, half the frequency. And then what happens is a 4-magnon scattering takes place. 4-magnon scattering, two incoming particles, two scattered particles, like the gas. And then all these magnons here, which are actually filled here at this pumping frequency, they can just relax via the scattering events. And if you do everything right, they form a magnon condensate here at the minimum energy state, which is just shown here with these two orange dots, what you see here. A very efficient way, and this is now really picked up by several groups, and it works remarkably well. And that is our way how to make the Bose-Einstein magnon condensates. Now, for today, I promised you to go to small structures. But let me just do a few things. Let me just summarize. What is the key element behind? The key element is that we have excess magnons in our system, because we can, for instance, use parametric pumping. So essentially, we are taking a full bucket of magnons and throw it into our magnonic system. And then we ask what happens with all these excess magnons. And we just have seen, due to the 4-magnon scattering, they trickle down and fill here the bottom states, resulting in Bose-Einstein condensate. And that is simply because we do everything so fast that the system cannot relax in the normal way. Or in other way, we don't have an open system thermodynamically. We have closed the system because we throw in the additional magnons via parametric pumping much faster than the system can relax. And this works very well. Now, I would like to show you that it can be done in a very different way, not by directly injecting, but by a process we call timescale injection into a confined system. And let me show you what's the trick behind this. And actually, before I do this, I should mention the work of the people who have done it, especially Michael Schneider, who is a PhD student, Alexander Sager, you probably know, and I guess you also know André Čumak, who has guided all this research, and he is now a professor at the University of Vienna. So let's go back. You have seen the Bose-Einstein distribution function. You have seen this curve. Mine, this is a log-log representation. And now let's simply assume that we increase the temperature. And you all know what happens if you increase the temperature. Simply, for thermal reasons, you have more Magnons in the system. And therefore, the distribution curve would look like this one here. And now let's assume we instantly cool down the system. Instantly means, for an experimental physicist, we cool it down much faster than the system can relax. And if we do so, then we have a problem, because if we cool down from T max to T min, then all these Magnons here in between are in excess. So we have to get rid of them. And of course, now you can ask, what will happen with these Magnons? Number one, what will happen is, of course, you have Gilbert damping. That is why I have put Sergio's 2003 paper here onto the front page of my talk, because it basically tells you that the Magnons at higher frequency relax faster than those at the lower frequencies. So after a while, we get an excess here. We also have the scattering process, in particular the 4 Magnon scattering process, and they essentially shift the weight here towards the lower frequencies. And you can throw it into a model, you can do numerical simulation, and what you find, again, you get a divergence in the population at the lower state, and that is fingerprint of Bose-Einstein condensation. This means you now can even do Bose-Einstein condensation with very little effort. All you have to do, you have to have a sample which you cool down very, very rapidly. And to do that, you have to go to the micro world. And here you see a good example. Substrate is GGG, gadolinium gallium garnet, which actually is a very good heat conductor, by the way. Here is yttrium iron garnet. We put some platinum on top because we can put a DC current through the platinum simply for the purpose of heating it. So there's no spin transfer torque effect in this particular system. And then we use Brillouin light scattering spectroscopy, a technique which is also available in Sergio's lab. So Sergio, you can repeat this experiment tomorrow if you like. And then we can measure what happens here with a Magnon at the laser focus. And then we can apply a current pulse, and the current pulse will heat the system. And if we switch off the current pulse, then the system will cool down very, very rapidly because of the very good thermal conductance of the entire system. And the GGG substrate just acts like a very, very good reservoir. So that is the experiment. And actually, if you like, you can even do it at home. All you need is just this particular sample. And you need to have a current pulse generator, which I think you find in nearly every lab nowadays. So it's not that you need a lot of equipment to do this experiment. So let's see what happens if you do the spectrum. That is a spectrum here in a false color picture of this yttrium iron garnet stripe. Then we see the fundamental mode. We see some peculiarities of a confined system, like an edge mode, not of interest here. We even see the first perpendicular standing spin wave. And now what we can do, we can apply a current pulse. You see as a current pulse, the system will heat up a little bit, so the expert notice that the frequency goes down a little bit. And now we can switch off the current pulse. And now watch what happens. What happens is that all the Magnons go here into the lowest state. Yeah, so we get a divergence here, like we have seen before in the experiment in the lowest state. So a fingerprint of Bose-Einstein condensation. And I will even now show you that we can actually prove experimentally that this is a Bose-Einstein case. To prove that, we take advantage that we can observe the fundamental mode, which we study here, and that we can also observe the first standing spin wave. That is just a very ordinary mode which travels forth and back between the surface and the backside of the sample, forms a standing spin wave. What we can do, I will cut the story a little bit short, we can approximately use the Rayleigh-Jeans distribution function, and then we can here calculate the chemical potential of the system simply by the intensity ratio between these two modes. They should have an intensity which is normally given just by the thermal occupation, given by the radial Jeans distribution function. And with this simple formula, we can estimate the chemical potential. And now see what happens. We repeat the same experiment like before. So we get the Bose-Einstein function. We get here the frequency of the fundamental mode. It varies a little bit because of a heating effect. We put in a lot of power. And here is the chemical potential. And there is no parameter for adjustment. There's an absolute measurement. And we indeed see that the chemical potential touches the minimum frequency here at the point where the Bose-Einstein condensate happens. So I think that is the best proof we can show that indeed the chemical potential matches the minimum frequency here in the experiment. Okay, this needs a little bit more proof, and what is very useful here in the field is numerical simulation. And Morteza Mohseni is a very talented PhD student who did it under the supervision of Philippe Perot and in a collaboration with Arne Bratasch, who also has a lot of experience with that. And I would just like you 2 or 3 view graphs how to do that. What he does is essentially putting everything we had in the experiment now onto a computer. So we have a Higgs stripe, we have a microwave antenna, if we would like to use parametric pumping. And then we get discrete modes because now the system is extremely small. So you see here, this is only 1000 nanometer, thickness is only 85 nanometer. So we get discrete modes. These are all perpendicular standing spin waves. Here is a fundamental mode. Here's a minimum where the Bose-Einstein condensation should happen. And for this computer experiment, again, he has used parametric pumping. So the photons decay into Magnons at half the frequencies, always in pairs. And that is how it is set up. And now let's see what happens in the experiment. And indeed, what we find here is now Magnons at half the pumping frequency. And now we wait a little bit so that the 4 Magnon scattering events can set in. And you see here now what happens. 4 Magnon scattering happens, and the Magnons are scattered up and particularly down. And you see already a lot of intensity showing up here. And now, if we wait a little bit more, then we notice that in the numerical simulation, we find Bose-Einstein condensation in the minimum state. So we can even now mimic Bose-Einstein condensation. And I can assure you that it's now an extremely useful experiment, especially if you want now to do the new applications, making qubits out of it. We need to manipulate qubits, and that is hard to do in the experiment, but in the computer experiment, we can always prepare these kind of experiments. Indeed, that it works very hard. You find out very well. You find out if you analyze the data a little bit more. Here is the spin wave amplitude, so the Magnon occupation number logarithmic scale as a function of time. And if we start the parametric pumping and switch it off here, you see very nicely how a condensate is formed. It decays, of course, because of some residual coupling to the phonon system, which you always have. If you look how the amplitude varies as a function of the microwave pumping current, you see characteristic thresholds like here for the parametric generation. So here's a threshold for parametric generation. Then you get another one at somewhat higher powers where the 4 Magnon scattering sets in, is also a nonlinear process. And then you see here's a threshold for the condensate formation. Here's the conditions that the chemical potential equals the minimum frequency is just fulfilled at this particular threshold value of the pumping. So you see we get a very intuitive picture out of these numerical simulation data. And that this is not only just a science fiction story. I would like to show you here with the first experiment we did really on very small structures. This is a 1 micrometer wide Higgs waveguide, 85 nanometer thick, so same parameters like in the numerical simulation, backward volume mode geometry. And indeed, we do the pumping over this period, and here we switch off the pumping, and again we get here the Bose-Einstein condensation, which is evidence here with this very high false color. And if we do the experiment, we get the characteristic formation of the Bose-Einstein condensate here with the maximum here a short time after the pulse has been ended. So much. Just to summarize, I wanted to show you the first experimental evidence that we can now create Bose-Einstein condensates by a new process, rapid cooling. The injection mechanism is originally incoherent, but it can be applied also to other bosonic systems. And I showed you that magnon condensation in microconduits can be shown using micromagnetic simulation. And just the outlook, this can now be used to create new ways how to use Bose-Einstein condensation in magnetic nanostructures. It had no time to talk about spin transport. We have several mechanisms how in such a BEC supercurrents can be created, Bogoliubov waves can be created. I had also no time to show you that the propagation can be non-viscose. And what I wanted to point out is that this opens now a new field, that we can make magnonic qubits, like you see here, that we find ways how to manipulate the qubits and to do the initial stages of qubit calculation. And that is, of course, a very exciting outlook, which we now have here in the field. So thank you very much for your attention.
Thank you, Professor Hillebrand. Let's hear Professor Hillebrand, please. Okay, let's move on to the next talk, which will be given by Professor Axel Hoffman. Axel Hoffman, until last year, was a group leader of the magnet thin film groups at Argonne National Lab. But a year ago, he joined the Department of Material Science and Engineering at the University of Illinois at Urbana-Champaign. His research interests encompasses a wide variety of magnetic phenomena, including basic properties of magnet heterostructures, spin transport in novel geometries, and magnetization dynamics. The title of Axel's talk is Hybrid Magnon Modes. Please, Axel. Is your microphone on?
So, can you hear me now?
Yes, yes.
Okay,
But,
sorry.
But okay, go ahead.
Part. Can you see the slides well?
Great, thank you.
Okay, very good. Thank you very much for the invitation. I'm really very honored to be part of the crowd here, honoring Sergio, who is really an outstanding scientist. I'll be happy to tell you some of the things that we've done with hybrid magnon modes lately. But really, here's what I want to start off with. I want to first tell you a couple of the things that I learned from Sergio, over the years. And then I'll talk a little bit about hybrid magnon modes, how they can be useful for coherent information processing. That job became so much easier after listening to Burkhard now, although he did steal some of my thunder, but oh well. And then I'll tell you some of the work that we've done in that respect, and given the time, I'll limit to the most interesting part, and then some conclusions. So the things that I learned from Sergio, well, the first time that I met him in person, well, in person, I mean, I was listening to a presentation from him, I would say, is the first time that I actually went to Brazil, which was a little over 10 years ago, for the National Physics meeting in Brazil, which was in Aguagil, Lindóia, at the time. And I remember this meeting very well. I was surprised to see Sergio in the program with an invited presentation on a very scientific topic, because I knew that at the time he was also the Minister for Science and Education. And I figured, oh, okay, well, he's going to talk about some science that, some of his students did, what do I know? But it turned out what he was talking about was what, Burkhard was just mentioning, his theory paper on Bose-Einstein condensation. And I was really kind of amused. He started his presentation off that he was leaning hard on the PRB editor to get this published in time, because he wanted it published before his presentation. And, see, it worked. It got published on the 11th of May, which was just the beginning of this meeting. The other thing that, looking at this paper, I was truly amazed that he did this himself at the time when he was busy with other things. But when I looked at this paper, I also liked this very much, that the author was grateful to the Ministry of Science and Technology. So he was thanking himself, but, well, I guess kind of. But the lesson that I took from this is, if you have administrative duties, that's not an excuse for not doing great science. So don't complain about whatever committees any of you might be on. You should still be able to have fun with science. So the next thing, then a couple of years later, we were doing some experiments where we looked at spin-Seebeck effects with antiferromagnets. And I'm not going to go in great detail, but what we did is we had some single crystalline manganese fluoride films. We patterned the heater on top, and then we measured, thermoelectrically generated voltages that were generated from this. And we could see some very characteristic voltage with magnetic field dependencies. And depending whether the magnetic field was perpendicular to the easy axis of the antiferromagnet or parallel, we saw very different behavior and a distinct spin flop field there. And so when we took this data, I figured, who could possibly help us explaining what exactly we were doing, right? And who comes to mind? Well, of course, Sergio, right? Because first of all, he had already theoretically thought about how spin-Seebeck effects come from magnon accumulations. But also, he had a lot of experience working with antiferromagnets, in particular manganese fluoride. And sure enough, Sergio developed a nice theory, just taking the well-known magnon dispersions of manganese fluoride and how the magnon dispersion changes as a function of frequency, so as a function of field. So at low field, you have two magnon modes that then split into two separate modes. And so as you increase the field, you start populating more and more these modes, and you get then an increase of this spin-Seebeck voltage, which really very much matches what we saw experimentally, in great detail, actually, which was kind of nice. But the thing I really want you to take away from this, so he published this theory of our data in January, and we published our data actually in March. So I guess what this tells you is, if you understand what you're doing, that's way much more important than when you're actually doing things. So, thanks to Sergio for helping us understanding what we were actually doing there. The third thing that I wanted then to say about what I learned from Sergio. So a few more years later, I came across this work from Sergio, where they looked at how when you take a magnon mode in yttrium iron garnet, if you lower the magnetic field, then what happens is this magnon mode may cross over with a phonon mode, and so the magnon may convert it into a phonon. And what they then did is, by looking at regions in the sample where the field was very low, they could see that the phonon mode actually has angular momentum associated with it. So the angular momentum from the magnon mode gets preserved in the phonon mode. And it was really a nice, elegant experiment. I liked it very much, as Sergio knows. But what impressed me really is, so here's this work in 2018, which essentially was a continuation of his PhD work, right? I mean, he has done these things like 50 years before, where he looked at magnetoelastic waves, how they vary in time when you change magnetic fields. Well, instead of using a time varying thing, you change now the magnetic field as a position. But, it's similar idea, really. So if you stay long enough, around long enough doing what you think, you can take your old ideas, recycle them, and sell them as something new. Well done. Anyway, so what this work really told me is that there's interesting things to do when you look at how magnons may interact with other excitations. And so that's what I want to talk about now, how hybrid magnon modes can be really useful and interesting for various things. So Burkhardt gave already a nice introduction how magnons may be useful in coherent information processing. Let me add a few more ideas on top of that. One thing that is nice about magnons is that you can come into a regime where you very strongly couple it to other excitations, let's say to microwave photons. And you can do this easier than with a single spin that you may want to use for quantum computation, because the coupling strength scales as the square root of the spins involved in your system. So just by having lots of spins in a ferromagnet that are all coupled coherently together, you can get much stronger coupling to the photon field than you could do for individual spins. Now, the next thing is that magnons can couple to all kinds of excitations. As you will see in my presentation, they can couple to microwaves, but they can also couple to light, like the BLS kind of data that Burkhardt just showed. Phonons, as what I just showed you earlier from what Sergio did, in the beginning of his career already. And of course, can couple to other spin degrees of freedom, other magnetic excitations. So there's a wide variability how you can use magnons to kind of mediate between all these different excitations. And then, this is kind of rehashing what Burkhardt just said. You can take advantage of the fact that magnons propagate as waves, and you can look at coherent interactions between different waves, and so it may allow you to do magnonic logic in some way. And lastly, what is nice is since microwaves are really very central to many ways how we want to implement quantum computation kind of ideas, there has been a lot of development how to make very nice integrated microwave circuitry. And so if you can now integrate your magnetic component into these devices, it allows you to think about doing things in an on-chip integrated fashion. And just some shameless advertisement for ourselves. If you like all the kind of things that I'm going to tell you about, if you want to have a better idea what it's all used for, we wrote this down in a very detailed fashion in this perspective article, which was published earlier this year. So all in all, magnons are really a very versatile vehicle to think about coherent information processing. You can use them in bulk form. You can use more integrated planar kind of devices, which I'm talking about here. There's various coupling mechanisms. You can have dissipative coupling. You can have non-reciprocative physics, spin pumping, all kind of these kind of issues. And you can couple it to various excitations from optics to phonons and so on. So there's a whole wide field of range that you can use magnons for these coherent processes. Now, ultimately, we want to do something in the quantum regime where we can actually look at individual magnons. And this has been even already demonstrated by showing how individual magnons can couple to an individual superconducting qubit via the photon field of a cavity. And you see this mode separation here between the qubit and the Kittel mode This was really a groundbreaking work fairly recently. This is really very hard to do. You have to go to very low frequencies, as what Burkhard just mentioned. I will talk about how you can learn a little bit more, how you can possibly do these kind of interactions, but at elevated temperatures where you're still in the classical regime. So the goal for us then is to look at how can we make new magnetic circuits where we integrate magnetic devices into a microwave quantum circuit kind of structure. And so this is where our work comes in, where we look at the on-chip integration of magnon-photon coupling. So magnon-photon coupling has been demonstrated by various groups before, but most of these previous demonstrations have been relying on bulk yttrium iron garnet samples that were integrated with 3D cavities. So here you see a picture where you see a macroscopic yttrium iron garnet sphere in a big 3-dimensional cavity. So this is nice. It allows you to do a lot of fundamental physics, including the type of work with the superconducting cavity that you saw. But it's not very amenable to a more integrated, complicated structure. So what we wanted to do is wanted to see if we can do this in a planar geometry. And for this purpose, what we did, we defined a superconducting resonator simply by geometry. We had two capacitive connections at the end of the resonator. And then we integrated a magnetic element, in this case, a permalloy stripe, in the center of this device. So for the photon system, our superconducting resonator is made out of niobium nitride. Niobium nitride is nice because it has a relatively high TC of 14 Kelvin, and we had all the technology for producing these resonators in high quality already in our group. And for the magnetic system, we used permalloy for simple reasons. First of all, it's much easier to integrate than yttrium iron garnet, which is problematic. Also, getting high quality yttrium iron garnet samples that work at low temperatures is hard, because if you have them on the typical gadolinium gallium garnet substrate, then the the GGG will have additional microwave absorption at low temperatures because it's a frustrated magnetic system. Now, the permalloy itself has a damping that's not as good as yttrium iron garnet, but as you see, it's good enough for our purposes. And it has the advantage that it has a much larger magnetization. So that will help in terms of getting strong coupling. Okay, so using this system, we then measure the transmission using a vector network analyzer together with an attenuator to keep the power nice and low when we do the low temperature measurements, and an amplifier for the output signal. So here you see the actual photograph of our sample. Going closer, here is an optical photograph. You see the permalloy stripe is integrated on the center of this resonator. In a cross section, you see that this permalloy wire is a little narrower than the signal line of our coplanar resonator, and it's electrically isolated by an additional layer of magnesium oxide. But it's very close to the signal line in an area of the resonator where the magnetic field lines are really maximized. So the first thing that we did is we characterized our superconducting resonator without the magnetic element. So here you see the measured transmission as a function of frequency measured at 1.4 Kelvin with a frequency, with a power of a few nanowatts. And what you see is we get a line width that's about a little more than half a megahertz at a fundamental frequency of 5 gigahertz. So we get a quality factor of almost 8,000. The next thing that is we did look at the resonator as a function of magnetic field, because we wanted to operate it in a magnetic field. And what we do see is that there's some hysteretic magnetic field dependence of the resonator frequency. There are some well-defined individual steps that you see happening here. And what this relates to is that we end up having vortices in the superconductor, and the vortices in the superconductor will enhance the inductance of the system, and thereby lower the frequency of the resonator. And so that's why you see these changes, these field-dependent changes of the resonator frequency. So the next thing that we did is then characterize the resonance of the permalloy itself. So we just measured the resonance frequency as a function of the applied magnetic field. This was measured still at low temperatures, but by very large power, so that the resonator is actually not superconducting anymore. And essentially what we then measure is just normal FMR in that sense. And so we can fit the FMR to a Kittel equation. We can look at the line width as a function of frequency. And from this, we can determine the damping, which is a little more than 0.01. It's not the greatest, but it's respectable. More importantly, we can get the Magnon relaxation rate, which is about 0.2 gigahertz. So almost 3 orders of magnitude higher than for the photon modes. Now, we can look now what happens when we combine the two things. So here again is the niobium nitride resonator without the permalloy. You see these field dependence of the resonance field, as I showed you earlier. And now if we have the permalloy stripe as well, what we see now is that at those fields where the Magnon modes crosses the frequency of the photon modes, we see a big change of the combined resonance frequency. And so essentially we see a mode repulsion with the mode going down here and an additional mode at higher frequencies appearing up here. So in this crossing region, we then have a hybridized mode of the Magnon hybridizing with this photon mode. Now, we can go to very high fields here where we really just look at the photon mode itself, and we can get the damping rate there. And we see just by having the permalloy device integrated with our resonator, we do affect the lifetimes of the photons in the system itself. So we get a Q factor of only 2,500. So it's a reduction by a factor of 3 from the unloaded device. But now we can also determine the coupling energy. So we know the energy of the Magnon mode, of the photon modes, and we can look at this cross-coupling, which is really due to the magnetic fields associated with the microwave photons. So here you see the same data plotted for just the photon mode and the hybridized both modes. Below here you see the line width of the hybrid modes also. And so we can analyze now the transmitted power using this equation. And so what we get from this is that the coupling comes out to about 1.15 gigahertz. And if we now calculate the cooperativity, which is the coupling squared over the Magnon and photon relaxation rates, we get a cooperativity factor of about 70. And so this tells you how many coherent interactions you can have in the system before coherence is lost. So if you wanted to do some coherent information processing, you do have to have a cooperativity larger than 1. And so 70 is actually quite respectable. So let's compare this to what has been done earlier with these more 3D bulk systems. So in our case, we can now calculate from this coupling constant, what is the coupling per individual Bohr magneton? Because we know that the coupling, the overall coupling goes as the individual coupling times the square root of the number of spins. And so if we take the volume of our sample, we get a coupling per Bohr magneton, which is about 25 Hertz. If we do the same and compare this to previous data for Yig-sphere, which is much larger in volume, what we see is that the coupling is much lower, namely almost 4 orders of magnitude lower. So by having this coplanar structure, you can actually get much stronger coupling. And so you can overcome some of the disadvantages of having lower quality resonators, both for the magnon and the photon system. But I should say this is not really the end of it. This is just one of the first implementations of these coplanar device structures. At the same time, when we were doing this work, similar work was done by Lu Xiaoliu at MIT, and using a different type of resonator design, they could optimize the volume of the magnetic system with the photon resonator even more and get a coupling that's even an order of magnitude higher than what we saw in our experiments. So using these coplanar structures is really fairly promising for the future. I want to just briefly mention a couple more things. We can easily modulate the strength of the coupling by changing the direction of the field. The data that I've shown you so far was with the field applied along the permalloy stripe. If we change the field perpendicular, well, then there is no coupling anymore because the RF field is now parallel to the magnetization. And you see that this hybridized mode goes away. Well, at zero field, there's something because then the field isn't strong enough to saturate the magnetization. But we can see that the coupling systematically decreases as we change the orientation of the magnetic field, as we would expect just from simple geometry. We can also look at how the coupling changes with the volume of our magnetic system. And indeed, we see that the coupling changes exactly with the square root of n as one would expect. Now, a last thing that I want to mention before I finish is when we go to high power, we can see some distinct nonlinearities in our excitations. And it turns out that this nonlinearity comes now from introducing superconducting vortices in our structure. And we see that the frequency shifts to lower frequencies because, again, the kinetic inductance increases and lowers the resonance frequency. But interesting enough is when we go to this nonlinear regime, we see that the mode splitting also increases. And so the interaction of the magnetization with the superconducting vortices actually leads to an even stronger interaction by about 15% enhancement. So there's maybe even some opportunity of using the interplay between superconducting vortices and magnetization dynamics to get more interesting magnon-photon coupled phenomena. So I want to briefly mention who did all this work. This work was done really at the end of my time at Argonne. So here you see my former group at Argonne. And really, most of the work has been done by this guy, Ely, who's really very talented young scientist. So you want to keep your eyes peeled for him. He's really one of the best I worked with. So here are all the various people. First and foremost, Ely. Tomasz Polakovic, who is right here, did a lot of the development for the niobium nitride type of devices. And you see lots of other people that helped with this work. So here's the brief conclusion. Magnons can be really very versatile information carriers, which can couple to many degrees of freedom. And what I showed you here particularly is that you can have strong coupling to other excitation modes, even in a compact on-chip geometry, which I think opens up a wide variety of new application things. And the nice thing about these magnetic systems is that this coupling then is widely tunable by various parameters that you have very much under your control. And well, I would like to finish this presentation, by wishing Sergio very happy birthday. And I think this is a much more realistic birthday cake than the one that Burkhard had earlier. So again, thank you very much for your attention.
Thank you. Let's cheer again our presenter. Okay. Now we are supposed to have a very short break. Is that right, Sidi?
Yes. 10 minutes break.
Okay.
Yeah, 10 minutes break.
After that, we'll continue with the scientific program or with Hughes talk.
Scientific program.
Okay.
Yeah.
Fernando,
Oi.
antes de eu falar, você me dá uma mão com o Sergio?
Sim.
Obrigada.
Okay, so we have a break now.
Okay.
Time for a coffee. Fernando. Ei, chefe, que legal. Finalmente.
Eu quero só fazer o testezinho rápido aqui. Aparece
aí.
Aparece a tela?
Calma aí, você tem que apresentar, né?
Espera aí.
No canto embaixo, lá embaixo, canto direito.
Espera aí.
Isso. Aí escolhe tela inteira.
Entire screen.
Aí você clica no meio da tela, onde está o full screen, né? E aí você compartilha, né?
Sure. Tá indo, eu acho.
Tá indo. Se abrir, pronto. Abre a apresentação só para... Pronto, aí. Bota no modo apresentação. Pronto, fantástico. Muito bom. Beleza.
Valeu, Fernando. Obrigado.
Agora você para de apresentar, né, para voltar à tela anterior.
Ok. Stop.
Fechado.
Valeu.
Bom, eu vou aqui e volto rapidinho.
Vou aqui também, tchau.
Fernando,
Hey,
também estou
Carlos,
aqui,
good seeing
viu?
you.
Você não tinha me visto.
Hi, Hoffman.
Bom,
Tchau.
How are things for you?
Fine.
Yeah, you look good.
Yeah.
Oh, hey.
Okay.
I was pleased to see you put Fibonacci numbers in your talk.
Yes, you understand me. 3, 5, 8.
Very good.
Okay. I will drink water.
Yeah, sure.
Pucha, como todavía está con dolor, ¿no? O sea que mi papá le dieron dolor al principio. El cáncer de pulmón da un dolor fuerte parece que en un brazo. Ya, aquí esta zona aquí, bueno, no sé si en la izquierda. Perfecto. Y mi esposa dijo, nunca más, ya no murió sin dolor. No me dio dolor, nada. No, por suerte, porque cuando él comenzó a tomar tramadol, la misma estaba tomando, pero parece que le hizo daño. El tramadol es morfina. El viejo mío no le gustó porque lo ponía droga y él no le gustaba. Estaba mierda. Así que por suerte después se le quitaron los dolores. Sí, yo me acuerdo el día que lo llamé y me dijo, que esto está buenísimo, ¿cómo es? No sé qué. Lo había llamado otros días atrás y estaba... Y ahí yo sospeché que estaba ahí. Y después se dio cuenta que estaba ahí. Por suerte, como le digo, después se le quitó el dolor. Pero pues, mi mamá después me contó, yo fui a verlo a él y fue 3 meses antes de Navidad y después de Navidad yo vi de nuevo. Y dice mami que se murió como 40 libras, o sea, más largo. Sí. Porque después pierde mucho el apetito y después no se ya se tiene intestino. Estaba en todos lados. No se te paraliza el intestino, no puedes comer bien.
Roberto, teu microfone está aberto, viu? Só para você saber.
A ver, vamos.
Fernando, Fernando,
Oi, filho.
o Rios vai falar, então, depois do Nissim. Né?
Isso.
O Antônio estava fazendo uma confusão ali, ou seja, eu acho que termina o Nissim, aí o Antônio sai, eu entro e chamo então o Rios, depois leio a mensagem do Mascarenhas, e aí você entra e mostra a mensagem do Fértil, né?
Perfeito.
Tá bom, Cid, eu entendi agora.
Ok, Antônio. Roberto, tudo bem, Roberto?
Estaba falando ahí con un colega que tengo una colega nossa aquí que descubrió que estaba muy doente ahí. E aí estava o microfone aberto.
Esse é um problema aqui.
É um problema terrível, senhor.
Tem muito ministro aqui no Brasil que já sofreu com isso.
Eu tava com medo de ser outro hacker, viu, Roberto?
Sério?
Oi?
Meu Deus do céu.
Puxa vida, olha,
O que estava No, que estaba falando, Fernando, é certo. Aqui tem uma reunião que o reitor fez com todos os estudantes, então ficou aberto para todos os estudantes da universidade e deu nisso também, deu nisso. Fizeram um
você já viu, então, isso aí? Para mim foi a primeira vez que eu vejo isso aí. A gente, durante todo o semestre, fez seminários, fez colóquio, e nunca aconteceu isso, né?
Ô, Cid, isso é muito... Cid, isso é muito comum na área de humanas. Tem muito. Inclusive, a do FEP saiu uma nota recente que eles estão tentando combater esse tipo de invasão, né? Porque tem atrapalhado as aulas. Né? E aí é muito comum, porque qualquer um que rateie um desses e-mails, ele entra em qualquer sala da universidade.
O Fittipaldi me disse uma coisa que, daquela teoria de conspiração, né? Ele disse o seguinte, olha, fulano de tal me disse uma vez que é muito provável que pessoas dos governos passados sejam acompanhados aí pela BIM ou coisa assim. Então, uma coisa desse tipo pode ter pode ser uma ação bem coordenada, né?
Pode ser, pode ser.
Hey, let's come back.
Já passaram 10 minutos?
Yes.
Marcamos 10 minutos. São quantos minutos?
Já passaram. Eram 16 horas quando a gente parou.
Faltam 3 minutos.
Falta aí homenageada aí, cadê o...
Tá bom, então vamos esperar.
Chairman!
O chairman ainda... Chesman. Eu pensei que você estava falando o chairman. O chairman ainda é o Antônio aí.
Eu entrei aqui, vi o Chairman aí com essa barba aí.
Ok, eu tenho que atender uma ligação aqui do Banco do Brasil.
Eita.
Eu pensei que o comandante tinha ressuscitado.
O homenageado já está aí, não?
Não.
Não, está a cadeira, está a cadeira.
Cadê?
Vocês estão indo, Antônio, à universidade já?
Tô. Sim. O Sputtering está funcionando a pleno vapor.
Eita, que legal.
Alexandre está aí, eu vi. Alexandre está por aí.
Alexandre está por aí, sim.
E
Joaquim, parece que vi ele também nos nomes aí. Aí está aí, pues.
Estou por aqui, Roberto.
Eita!
Tá bem, Roberto?
Muito bem, obrigado. Cara.
Não é um hacker infiltrado aqui não, viu, Antônio? Sou eu.
Que loucura é essa, né?
Ô, Antônio, isso está sendo cada vez mais comum. Em São Paulo, eu vi 2 seminários acontecerem isso.
Não sabia, não. É a primeira vez que eu vi. Eu achei estranho quando o Pedro Carelli começou a falar, aí surgiu um palavrão no meio.
Foi.
Aí eu digo, ele está num bar, num restaurante, alguém pode ter dito um palavrão na mesa ao lado. Né? De repente, começou aquela loucura. Né?
A Maria Vaz mandou um e-mail durante a apresentação dizendo que realmente está muito comum na área de humanas, né? Mas que para ela foi a primeira vez ver na área de exatas, né, acontecendo, né? Não é
Mas
muito...
é sempre na mesma plataforma?
Uhum.
É sempre no acontece?
Belita, eu dei uma pesquisada na internet aqui, diz que ocorre em todas as plataformas. Então
Mas
você tem que convidar as pessoas e cada uma tem que confirmar por e-mail para receber um código associado àquele e-mail.
Isso, é a única, a melhor forma é essa, a única é.
Mas o Zoom permite isso. O Meet eu acho que não permite.
Toda vez que eu abro uma aula em Zoom, a próxima é outra senha, então já não, é mais difícil, na verdade. Não, impossível não é, mas mais difícil.
Sérgio voltou aí, não?
Voltou.
Podemos começar? Reiniciar?
Estou de volta aqui, tomando um cafezinho.
Okay, let's move on to the next talk, which will be given by Professor Roberto Rodrigues Soares. Roberto now is the director of the Institute of Physics, da PUC, in Chile, Santiago. And Roberto works with magnetic materials, magnetic properties of ferromagnet in films and multi-layers, surface effects, and exchange interactions in magnetic nanostructures, spin current phenomenology in magnetic nanostructures. And his talk is on magnetic spin current in ferromagnetic and anti-ferromagnetic insulators. Roberto, please. You may upload your presentation.
Yeah, how can I do that? I don't see.
Roberto, Eduardo Padrão.
Roberto, na barra de baixo, no lado direito, tem apresentar agora.
Isso, mas...
Aí você clica nele, aí vai abrir uma janela, você escolhe apresentar a tela inteira.
Ok.
Aí você clica no meio da tela e aí compartilha.
Ok.
Tá usando Macintosh?
I'm working in Zoom, so this is new for me.
Tá usando Macintosh, Roberto?
Não precisa não. Isso aí é do...
Macintosh é que tem uma complicação enorme. Ok, it's there.
Are you see my presentation? No.
Você fechou ela, você destruiu ela. Abra de novo. Mesma coisa.
Não?
Não. Vai embaixo agora na sua barra e clique no PowerPoint lá que você vai apresentar.
Ok.
Aí, pronto.
Ok. And now?
Okay. Sim. Yes.
Okay, Roberto.
Okay.
Thank you.
Well, thank you. For me, it's a great honor to be here. Well, I will talk. This talk will center in 7 years of intense collaboration with Sergio and your group in Recife. So, but today I want to dedicate this presentation with a lot of spins to my dear Professor Sergio Rezende, the head of this incredible group. So this is the outline, all that I learned from Sergio. First, I will define what is a spin current. Before that, I will talk about the magnetic spin current in ferromagnetic and antiferromagnetic insulators. Finally, how can I measure it through the experiments? Okay, let's begin with the most important question. What is the spin current? Well, spin is angular momentums. So when you are talking about spin current, you are talking about the current of angular momentum. To better understand this, let's begin with the charge current definition. Suppose that you have a box, and inside the box, the charge density charge is changing in time. So if you invoke the charge conservation, you need to say that there must be a charge current that mathematically you write through the continuity equation, where JC is the charge current, or the charge density current. But imagine that instead of the charge density is changing in time, what is changing is the spin angular moment. So, well, you need to invoke the conservation of angular momentum, and in this case, you need to say that you have a flux of angular momentum that you write with equivalent equation, with the equation, the conservation of angular momentum, where G S is now the density current, but spin density current. Note that in this case, spin up and spin down electrons are flowing in opposite directions. Okay, but now the problem is that we are working, or we will work with ferromagnetic insulators, and in ferromagnetic insulators we don't have electrons flowing. So how to understand the flux of angular momentum in this kind of material? Well, in a ferromagnetic insulator or in a ferromagnetic materials, you have collective deviation of spins of angular momentum or magnetic moments. This collective spin deviation, we call it spin waves, whose quanta are called magnum. So in a ferromagnetic insulator, the spin currents are carried by magnums. Okay, from the proper definition of density current, and we are talking about a current of angular momentum, you write angular momentum per time through the area. So if you multiply above and below by the length of the magnums, the diffusion length, here you have here you have velocity, here you have angular momentum, and this is the volume. So from the heuristic point of view, you can say that the spin density current of the angular momentum current is number of magnums. This is the carrier. Per angular momentum, this is what are you transporting per its velocity. This is the group velocity. For example, if you write the particle density current for electrons, the density current for electron is where you are moving charge, concentration of electrons, and the velocity of what you are moving. It's basically the same concept here. So okay, but now imagine that you have an antiferromagnetic insulator. Again, the question is what we understand by a spin current in this kind of material. The problem is that antiferromagnets are more complicated. For example, you can think in material that in which you have two atomic sublattices with magnetic moment pointing in opposite direction. But if we think in the same point of view of the ferromagnetic insulator, here, for example, I am showing you what is happening in one of the sublattices of the antiferromagnetic insulator. If you take into account two sublattices, so for example, in this case, you have one sublattice with an amplitude of oscillation greater than the other sublattice. So at the final, you have angular momentum that is propagating by the spin wave. We call it alpha mode. You can also have the opposite mode, in which the other sublattice, the sublattice that here is below, is oscillating, or the magnetic moment in this sublattice is oscillating with amplitude greater than the other. So, okay, call it beta mode, and the spin current you write as a combination of the current of the beta mode and the current of the beta mode and alpha mode. So it is almost the same thing. A little more complicated, but almost the same physics. Okay. For example, in this kind of antiferromagnetic insulator, manganese fluorine, you have the Hamiltonian in this kind of antiferromagnetic insulator. The frequency versus wave number is degenerate when the external magnetic field is zero. And this is because you have symmetry. To break the symmetry, you can put an external magnetic field, and you break the symmetry. And in the first case, the number of magnons of the alpha and beta mode equal, so the spin current is zero. And in the case in which you put an external magnetic field, you break the symmetry, and the spin current is different from zero. Okay, this is the way in which we can write and understand the spin current in this kind of material. But we need to detect the spin current, and for that we need to transport angular momentum, and we do that in bilayers composed by ferromagnetic insulators and normal metal. For example, imagine that you have a ferromagnet in ferromagnetic resonance. Okay, now you are pumping angular momentum with the magnetization. When the magnetization of the ferromagnet is precessing, you are pumping angular momentum to the normal metal. This metal can be platinum, tantalum, palladium, etc. So you have to write now the angular momentum conservation, the z component of the total angular momentum must to be equal to the relaxation rate, the flux of angular momentum to the normal metal. And then from the flux of angular momentum out of the ferromagnet generates relaxation on the magnetization. So from this equation, if you consider that this is constant in the volume and this is constant in the area, in the surface area, you can write the change of the magnetization of the z component of the magnetization in terms of the flux of angular momentum that is flowing. You are pumping angular momentum to the normal metal. Well, now if you write the movement equation, the Landau-Gilbert equation, we know that you have this equation govern the precession of the magnetization. So the term that govern this precession is the torque that the field, the external field is provoking. The other, you need to take into account the damping. The Gilbert damping you can write in this form, and the new term, this additional damping that I was talking to you in the last slide, is proportional to the current of angular momentum, or the spin current. This is the spin pumping current that we pump to the normal metal. And it is possible to demonstrate that this current can be written in this form, and is proportional to angular momentum, the spin conductance at the interface. Okay, so well, now we have a model. I will talk about the model that we developed from describe the Magnum spin current from the spin-Seebeck effect. The spin-Seebeck effect, in the spin-Seebeck effect, you induce a temperature gradient in the sample. Remember that we write the density, the spin current density in terms of the number of magnums. The number of magnums, you can write it in terms of an integral. This is the magnum population. The magnum population depends on the temperature, so it is possible. Here is easy to understand that when the system is out of equilibrium, this term is proportional to the gradient of the temperature. So in our model, we demonstrate that the magnonic spin current, the spin current carried by magnons, is proportional to the temperature gradient. The spin current in the ferromagnetic insulator or antiferromagnetic insulator, when you put here a non-magnetic material, is pumping, and you can detect it. But to detect the spin current, we need to talk about one phenomenon. I need to talk first about the spin Hall effect. In the spin Hall effect, in the spin Hall effect, a charge current, when a charge current circulates in a paramagnetic metal, it is generating a spin current or a transverse spin current. This is the relativistic effect. Okay, the inverse effect, the inverse spin Hall effect, is that in which a spin current generates a transverse charge current. In the spin Hall effect, a charge current, you have a charge current here, generate a spin current, a spin with opposite, the electron with opposite spin flowing in opposite directions. In the spin Hall effect, and spin current, for example, in this case, you are inducing a spin current by the spin-Seebeck effect. This spin current is pumping inside the normal metal, entering in the normal metal. In the normal metal, all generates a transverse charge current that you detect with through the nanovoltmeter in the laboratory. So this is a spin current direction. This is the polarization of the spin current, and this is the charge current generated. We precisely in 2005 in my PhD, when we are working in this problem, we discovered this effect. But even though we cannot explain it properly, we have not a very good explanation. So it appeared in this other paper. But in this paper, we pump a spin current in non-magnetic metal. This spin current polarized in this direction generates a charge current in the transverse direction that we detect here with another multimeter. Okay, so let's go to the experiments. For example, here in this experiment, by ferromagnetic resonance, a spin current polarized in the Z direction is pumping into the non-magnetic metal by the inverse spin Hall effect that I told you later. it is converted in a charge current and detected by a voltage in induced voltage. So here, this is the polarization. This is the spin current, the density of the spin current that is flowing in this direction, and this is the density of the charge current density. If you change the polarization, you expect that this change sign, so the charge current also change in sign. So this is wrong. This is for this side, and this is what we observe in the experiment. Know that when we rotate the magnetic field, the sign of the voltage of the induced voltage also change. This another experiment is in this another experiment we induce the spin current by the spin sig effect. Okay, we induce a gradient of temperature gradient in the sample. This temperature gradient generates a magnetic spin current in the ferromagnetic insulator, yttrium iron garnet. This current is pumping to the non-magnetic material and is detected like a voltage. The same phenomena. The difference here is that the current is generated by the temperature gradient. If you note, when you put, for example, the field in this direction, suppose that the sign of the voltage is positive. When you invert the field, the sign of the voltage also changes to the negative value. The other thing is that we are demonstrating here is that the spin current is proportional to the temperature gradient. When you put a temperature gradient in one direction, you have this slope. When you invert the temperature gradient, you invert the slope of the line. So this is in concordance with our model. Okay, here it's almost the same experiment, but I put the slide here to demonstrate you that this kind of experiment serves as a probe to characterize magnetic materials, like, for example, antiferromagnetic materials, metallic antiferromagnetic material like iridium manganese. Okay, but we need to move on to prove that the model also describe the dependence, the thickness dependence with the ferromagnetic insulator. So this is what I show you here. We have all the recipe. Yeah, we know that the spin current could be generated by the temperature gradient. Okay, this spin current is pumping to the normal metal by the inverse spin Hall effect. A voltage is induced. So all that you need to know to do now is to put the boundary conditions to the spin current. The boundary condition here, the spin current here is 0. The spin current here must be 0, and here you impose the continuity of spin current. And we can demonstrate that the spin current is proportional to the temperature gradient to the spin conductance here at the interface, and there are a factor that depends on the thickness of the ferromagnet. We obtain this expression that we show you in the next slide that fit very well the experimental data. So the model, the magnetic spin current model to explain how the spin-Seebeck effect, how we can explain the spin-Seebeck effect in this kind of material works very well. Now, this is the last slide. Here, I show you again the model, but now we are using here an antiferromagnetic insulator, nickel oxide. And what we show you is that when you have antiferromagnetic order in the antiferromagnetic material that we demonstrate here with the chain bias, when you break the chain bias, or when you don't have a chain bias, you are destroying the antiferromagnetic order, and the voltage, the induced voltage by the spin-Seebeck effect is zero. Different from this part in which you have antiferromagnetic order, you have when you put a magnetic field in one direction and invert the magnetic field, you change the sign, but know that we are observing a clear signature of the magnonic spin current induced in the antiferromagnet. So my conclusion is that our model of the magnonic spin current model explain the spin-Seebeck effect in this kind of material. The other conclusion is not very scientific, but it's very powerful, is that Sergio was right, because at some moment I feel that the model doesn't work, but Sergio always has this long-term vision. So Sergio was right. Well, Sergio, muito obrigado pelo que eu tenho aprendido com você. And I feel like a parasite, because I am only learning. Thank you.
Okay, thank you, Roberto. Let's cheer, Roberto. Okay, let's move on to the next talk, which will be given by Professor Carlos Chessman. Carlos Chessman is from the Department of Physics at Federal University of Rio Grande do Norte in Natal. Chessman works with magnetic and semiconductor nanostructures, including magnetic films, multilayer phenomena. And Professor Chessman is very actively engaged with development of scientific instrumentation. The title of his talk is enigmatic: 30, 50, 80, magnetism. Go ahead, Chessman.
Thank you, Antônio. Roberto, você ainda está apresentando aí, tem que sair, né?
Eita! Sei tudo esse negócio.
Estou aprendendo também.
Agora terminou?
Terminou. Tá ok a minha aí, apresentação?
Yes,
Hello?
yes, it's okay.
Yes.
It's okay, Antônio?
Yeah, tá okay.
Okay. My colleagues, I prefer to speak in Portuguese, but the text is in English. In fact, I am very nervous. Sorry. 30, 50, 80, magnetismo. Bom, é uma apresentação relativamente rápida. Eu vou falar dos laboratórios aqui de Natal, as contribuições científicas que eu tive com o Sérgio e as que ele fez acontecer logo em seguida, uma parte da minha vida atual, que é esses experimentos portáteis, né? E a explicação desse título aí. Então, hoje em Natal, nós temos um time de magnetismo, né, de 10 pessoas. 7 trabalham na área de nanoestruturas, né, e 3 trabalham nos sistemas fortemente correlacionados, né? Temos também uma equipe de 3 técnicos de laboratório, atualmente 2 pós-docs, 9 estudantes de doutoramento, 2 de mestrado, e nessa última década nós tivemos já a formação de 18 doutores e 18 mestres. Isso é um grupo relativamente grande. E a gente tem hoje uma infraestrutura relativamente muito boa. Todo esse aparato você pode ver virtualmente nessa página aqui, onde a gente descreve os equipamentos, as pessoas, as últimas publicações, as últimas orientações, tudo. Eu vou passar aqui e mostrar algumas fotografias dos equipamentos, né? Alguns são tipo homemade, como o efeito que é magneto-óptico, o VSM, que é a amostra vibrante, né, que já é um da Lakeshore, adquirido recentemente. Aqui o sistema de Sputtery, que tem até 5 alvos. Como esse sistema é muito comum em todo o mundo, eu tirei uma fotografia aqui para mostrar que esse equipamento está aqui em Natal. O equipamento que a gente tem mais sofisticado e relativamente caro é o chamado PPMS, que é o equipamento da Quantizide, né, que é uma central de medidas. A vantagem desse equipamento nosso aqui é que ele é o que chama de cryogenic free. A gente precisa só de um cilindro desse, de cerca de 8 a 10 metros cúbicos de hélio, a cada 6 meses, para poder funcionar todo o sistema de campo magnético, que vai até 14 Tesla, ou também podemos ir até 50 milikelvin. E o xodó é esse equipamento da Brook, que é um espectrômetro de ressonância ferromagnética, bem compacto e com a cavidade cilíndrica, né? E tem um Q, Antônio, que vai até da ordem de 9.000. Né? De forma que nessas últimas 2 décadas, os investimentos aqui na universidade, no laboratório de magnetismo, foram da ordem de 5 milhões. Prédios e equipamentos. Bom, passando a contribuições científicas aí, a primeira grande participação que eu tive com o Sergio Rezende foi no primeiro artigo de doutoramento, que foi uma análise teórica experimental de multicamadas ferromagnéticas, no caso, tricamadas, ferro, cromo-ferro, né, crescidos nessa estrutura 100. Curioso é que eu passei o dia tentando fazer o ajuste dos dados experimentais com o modelo que já havíamos construído, né? E a gente não conseguia, né? Nisso chega o Sérgio, vindo lá do então governo Miguel Arraes, com aquela bolsazinha dele, e diz: tenta colocar aí 30% de biquadrático com relação ao bilinear. Parece que a luz se veio. E rapidamente a gente conseguiu ajustar 4 dados experimentais: curvas de magnetização, de magnetoresistência, ressonância ferromagnética e espalhamento de luz brilhante. E por isso o artigo foi tão rapidamente aceito e, por incrível que pareça, sem nenhuma sugestão dos referis. Esse foi o primeiro grande resultado. Na sequência, eu já tinha 5 artigos durante o doutorado, né, e pedi o Sérgio para iniciar a escrita da tese propriamente dita, né? Aí eu me lembro que ele disse: não, você precisa preparar um artigo só seu. Você precisa ter a ideia, pegar os dados, fazer análise e escrever. E ele disse: eu vou ser o revisor. Assim você completa o treinamento do doutorado, né? E com isso você demonstra que tem independência científica. Curiosamente, em pouco mais de uma semana, eu consegui fazer o análise dos dados que a gente tinha com biquadrático, né, e chegar a uma modelagem de como medir esses acoplamentos. Né, e consegui, digamos, ter essa independência. Né, e isso, até hoje, eu uso como aprendizado. Ou seja, para ser doutor, precisa demonstrar essa independência conforme as orientações do Sergio Rezende. Na sequência, um resultado interessante foi durante o meu sabático lá no Argonne, tendo, inclusive, o Sérgio feito o intermédio para que eu fosse para lá também com o colega Axel Hoffman. Uma ideia que eu já tinha tido durante o primeiro pós-doutorado aqui em Natal, antes de ser efetivado, né, que eram as multicamadas tipo Fibonacci. Lá no laboratório, eu consegui preparar as amostras, que eu havia pensado cerca de 10 anos antes, né? E fiz toda a análise de medidas, né? Demonstrando que, estando em um bom grupo, um grande grupo, a gente é capaz de realizar as ideias rapidamente. E esse resultado tem a participação do Pearson, que é uma pessoa formidável, e o Hoffman também, que é um grande cientista. Por fim, das contribuições científicas, tem esse Scientific Reports. Esse daqui é um resultado bastante interessante. Um filme nanométrico de ferro cobalto boro, no qual a gente aplica campo magnético, gradiente de temperatura, né, e torção, para descobrir sensores que a gente possa fazer aplicação para um sistema chamado touch. Então, a gente precisa medir simultaneamente voltagem, que seria o efeito o efeito Nernst anômalo, né? Aplicar campo magnético, variar a temperatura, a gente varia aqui com um sistema que a gente chama uma placazinha Peltier, né? E fazer a torção, que é um sistemazinho mecânico. Né? O que foi que a gente conseguiu realizar aqui? É que esse material, crescido de uma maneira especial, o eixo de anisotropia pode mudar. Ou seja, ao aplicar a torção e outros parâmetros, principalmente, né, o eixo fácil passa a ser eixo duro e vice-versa. Ou seja, isso é um ótimo dispositivo para sistema tipo touch. Passando agora para a parte mais atual, que são esses experimentos portáteis. Um grande incentivador dessa parte, que eu me lembro, era o professor Cid. Né? E hoje a minha bolsa de pesquisador do CNPq, tipo desenvolvimento tecnológico, é exatamente isso. Nessa linha dessa nova filosofia chamada IO, que significa, em português, Ambiente de Aprendizagem Científica Investigativa. Por exemplo, aqui tem uma sala no MIT, uma fotografia, onde você vê que não é uma sala tradicional, é uma sala bem diferente. Telões com conexão à internet, bancadas, onde as pessoas vão fazer os experimentos. Ou seja, ela é centrada, basicamente, na observação experimental e nos testes experimentais. Todo o processo diagrama desse chamado IO tem a ver com isso. Né? E, como eu falei, isso começou em também uma universidade americana, mas se expandiu em várias outras universidades, inclusive da Europa e da China também. Ou seja, aprender ciência fazendo experimentos. Uma ideia que é bem interessante, que é exatamente onde hoje está o Hoffman, é esse pequeno dispositivozinho aqui. Ele aqui tem todo tipo de sensor para você fazer todos os experimentos de mecânica. Acelerômetro, medidor de velocidade, um piezoelétrico para funcionar como lead hook e tudo. E já está, inclusive, à venda na Amazon. E é bastante interessante o uso dele. Nessa ideia de minimalista, né, é uma contribuição que a gente está dando com essa bolsa do CNPq, montar esses experimentos. Todos eles em uma pequena caixa. As dimensões da caixa seguem mais ou menos um livro, okay? E a ideia é que o estudante, o professor, possa realizar o experimento na própria sala de aula sem necessidade de uma grande infraestrutura de laboratórios. Ou, se precisar, ter em vista a pandemia, levar e trazer esse material para casa, né? Tendo os devidos cuidados, por exemplo, para eliminar as bactérias, utilizando, por exemplo, uma lâmpada ultravioleta. E você incide sobre a caixa antes e depois do uso. Então, segue essa ideia minimalista e pode ser utilizado amplamente com essa ideia do IO. Aqui tem, por exemplo, um que realiza as leis de Newton, né? Ou, especificamente, como a gente bem sabe, é um legado também da lei de Hooke. Então, você pode fazer associação em série, ou em paralelo, ou mista, de molas, né? E o estudo é semelhante aos resistores na parte elétrica. Lá, ao invés de utilizar a lei de Ohm, utiliza a lei de Hooke, ao invés de utilizar as leis de Kirchhoff, você utiliza as leis de Newton. E o procedimento é bem semelhante, para você entender a física disso aqui. Outro que tem a ver com essa área que a gente trabalha é esse magnetismo básico, uma série de dispositivos que você vê como o magnetismo de uma pedra natural, uma rocha, né? Magnetita, modifica a bússola, ou uma bobina, através de um curto-circuito, você modifica também e vê que a bússola modifica. O interessante aqui é que essa rocha magnetita, né, é de uma mina aqui próximo da cidade onde eu nasci, que fica a 200 quilômetros de Natal, uma cidade chamada Jucurutu. Hoje eu trabalhei, hoje não, para captar, coletar essa, que eu fui na mina e fiz a coleta diretamente. Eu tenho hoje quase uma centena de quilos de magnetita. Se alguém precisar de magnetita natural, retirada diretamente da mina, a gente tem. Um outro experimento que esse, digamos, que faz mais sucesso, né, professor Anderson, que é essa placa metálica e as lentes cortadas por impressora laser, né, de acrílico, e com a mantazinha magnética você facilmente consegue reproduzir todos os experimentos que você pode montar com as leis da ótica geométrica. Espelhos, lentes, prisma, espelho côncavo, convexo, ok? É fácil de manusear, né? Tem o feixe de laser, na verdade são 2 feixes de laser para você poder ver a focalização ou a desfocalização. É o que a gente está chamando de física experimental in the box, in the small box. Bom, por que essa escolha do título aí? Efetivamente, olhando as datas aqui, a gente tem mais ou menos 30 anos de implementação do início dos laboratórios de magnetismo aqui na UFRN. 50 anos faz que foi iniciado a montagem dos laboratórios de magnetismo na UFPE com a vinda do Sérgio, né, para o departamento de física. E agora culmina com essa grande data, né, 3 de outubro de 1940, Sergio Rezende, né, e por isso o magnetismo. Ou seja, invertendo a ordem, tudo isso com certeza aconteceu depois do nascimento e das realizações do Sergio Rezende. As últimas palavras, né? A primeira vez que eu tive contato com o Sérgio, próximo, né, era uma apresentação de um sistema de suspensão ativa, um espalhamento de luz brilhante. Isso, acho que no final de 93, pelo que eu me lembro. Né? E eu fiquei impressionado porque Sérgio batia na mesa, né, entusiasmado, e repetia: olha para o sinal do osciloscópio. O sinal não oscila. A base do equipamento não vibra, né? Mesmo ele tendo batido na mesa. Né? Aquilo me impressionou, mostrando que era uma apresentação não típica, né, de um seminário e que tinha realização experimental. Né? Bom, aí eu acabei mudando de ótica, que eu fazia o mestrado lá com o Tabosa, e fui trabalhar no magnetismo, né, com o Sérgio e o Antônio durante o doutorado. Né? Eu costumo dizer, eu já conhecia Sérgio sem Sérgio saber que eu me conhecia, que eu existia. Isso é típico de pessoas famosas, né? E o fato de Sérgio ser famoso, né? Aí acontece isso não só comigo, mas com diversos colegas, né? Para mim, Sérgio, eu te considero um exemplo que a gente deve seguir. Não sei como, além de ser um ser humano formidável, né? É um cientista majestoso. Né? Muito obrigado, Sérgio. Vida longa para você. Obrigado,
Okay.
pessoal.
Thank you, Chesma. Let's cheer. Okay, we have to move on. The next talk will be presented by Professor Eduardo Fontana. Eduardo Fontana is professor in the Electronics and System Department at UFPE. Eduardo is engaged in research and teaching activities in the fields of electromagnetic theory and applications, bioelectromagnetism, optical instrumentation, optical fiber sensors and devices applied to surface science resonance. So his talk will be magnons in magnetic semiconductors. Eduardo, please, you may upload your presentation.
Thank you. Can you hear me?
Yes.
Just a second. Can you see my screen?
Yes, yes, great.
Well, I have been away from this this field of knowledge for almost 40 years now. So I'm happy to know how the things evolved since then. So I'm going to just talk about some qualitative aspects of my work and my interaction with Sergio from almost 4 years ago. That's the broad title, Magnums in Magnetic Semiconductors. But specifically, I'm going to talk about some landmarks of the master work I did on investigating the magnums in selenide, chromium and cadmium selenide, which is a magnetic semiconductor. That's the summary of the talk. Just gonna make a only brief comment on my first interaction with Professor Rezende, and then I'm going to go on to show some aspects of the work that I carried out and some concluding remarks. In early '80s, I was graduating, and then in the last semester, there was a position in the microwave laboratory. And this microwave laboratory was in the electrical engineering department at Federal University of Pernambuco, in our university. And Sergio had an interaction with the department. He built this very nice laboratory. There was a position for one IC internship. And I just, I was interested in doing some scientific initiation. In fact, I was only doing, teaching assistant prior to that. In the last semester, prior to my graduation, I wanted to start some scientific, learning. And then there was this position in the lab. And it was just new by chance, only one position, and I was immediately accepted because there was nobody else. So the work was comprised to, Sergio was in the magnetism area, but because he was involved in the electrical engineering, he wanted to make applications of magnetic materials, and the one application was to build. He was doing some work with my colleague before, who was developing a EEG oscillator. And for my, internship, he proposed me to try to build resonance isolator for the X band. The effect is based on the resonance effect, which is non-reciprocal. If you have a moving wave on one direction, it interacts with the processing magnetization. If you have a wave going to the opposite direction, that if you have a circular polarization not aligned with the procession, it does interact. So because of that, you have high absorption in one direction, you have negligible absorption on the other one. And the task, I have this relation between frequency and applied field, because the zero magnetic factor is about 2.8 gigahertz typically per Hertz. Then you have strong interaction in the microwave, as you guys all know, for a typical lab field of 3 kilohertz. Then the idea was to build this device. These devices are found, in those companies that make microwave devices. They build this, but our test was to position the ferrite slab, in the correct position where the effect has the maximum contrast. And it was very difficult to position this. It was very artisanal. We did this and measure the response until we find the optimum position. Somehow we had to fix this magnet with the proper field that saturated the ferrites in the, and then we were able to do it. Okay, so that was my work, my internship. It was very interesting work. I liked a lot of electromagnetics, and I could see in action in this work. Well, after that, in my master, we I mean, Sergio proposed to investigate magnons in cadmium and chromium selenide. I think that's the name in English. I'm not sure. Which is a magnetic semiconductor. And the idea was that it could enable magnetic control of electron transport for another device. And the research on these composites and these materials started in the early 60s. And this material has typically a key heat temperature of 129.5 Kelvin. So below that, they have magnetic properties. And conductivity is typically on that range. It's a good resistor, but it can be changed through doping or crystal growth. And the objective of this of this work was to characterize the dispersion and elucidate magnum relaxation mechanisms for low and high wave vectors, and as a function of temperature. The samples were grown by Dr. Gibart in France, and Professor Marcílio from the physics department, who also worked with Sergio, was the person who prepared those very precise spheres with a very small diameter, 0.5 millimeters. And I just wanted to show you, I mean, it was very interesting for me to revisit my master dissertation. I just found it. It was in my parents' parents' house. I thought I had lost it, but it was there, preserved. And I struck some diagrams that explain the scope of the work, the results that we obtained. Magnetic excitation is done by parallel pumping, which is the RF field is applied on the same direction of the static field, and if you start to increase the RF field, you start distorting the angular momentum, and then this distortion yields after a certain threshold two counter propagating magnons, and typically the wave vector that you produce is a function of the applied field, and the frequency of the magnet is half of the pumping frequency, and also the line width is proportional, to the threshold field, to threshold RF field. So if you measure the threshold, you are measuring the line width. If you measure if given the frequency, the frequency of the magnet. Okay, it's always fixed, and you change the wave vector by changing the study field. So you can by doing that get the dispersion relation and the dependence of the damping with the wave vector. I mean, all I'm saying, I'm sure everyone knows. Okay, but I mean, since I've been away from this for almost 40 years, I was revisiting those concepts. It was very interesting to know. This is a setup that we employed to observe the parametric excitation of magnets. We need high power, so we have a klystron. Okay. And the klystron was modulated. There's a modulator there. Well, this modulator produces pulses that are 5 microseconds in this case wide, and because we don't want to hit the sample, And then you go through a traveling wave tube that produces an output of 3 watts continuous wave. I mean, if it was a continuous wave, I can control the power by, this attenuator that we have. Then we combine, we send the part was into a cavity between a magnet, then with the circulated part comes back, then we balance the input with the reflected signal from the cavity. Then any imbalance due to some change in the cavity Q is going to be detected as changing signal here. And that's essentially the setup that we use. This is the original drawing of my master's dissertation. I mean, in those times, the drawings were made by hand by a drawer from the physics department. I think it was Carlos, his name. In fact, I met him. You can hear me? Oh, okay. I had some. Okay. Can you hear me? Yes.
Yes.
Okay.
It's okay now.
I think it's my. I think it's here. Okay. And as I was saying, I met Carlos. His name was Carlos. Does anybody know that? I'm not sure. But I mean, I met the drawer in Recife Antigo about 3-4 years ago, I think. So this is because the effect could only be observed at low temperatures, and we wanted to make measurements on varying the temperature, going down to liquid helium temperature. So we have this super vary temp with helium, liquid helium. You have some sleeves of vacuum and nitrogen, and you could control the flow of gas, cold gas to the sample, and by proper, control on the heat. Oh, sorry about that. Let me just go back here. Where was I? Okay. Yeah. So this is another aspect. I was talking about the temperature, but I'm going to talk here. So this is just a control of the iris to change the coupling of the input wave guide. There was a string, okay, which could be actuated externally. And we had this heater at the end of the system down the cavity. And by heating we could control the temperature, have a temperature sensor here. And this is the control of the sample, because we also measured the dependence of the effects on the orientation, the crystallographic orientation. And so this is the sample is on sapphire tip. This is going vertically from the plane. And I am very proud to have used this mechanism here to rotate the sample, because this was extracted from my guitar. And, so it could rotate this worm gear here, which came from the guitar, an old guitar that was not used anymore. So, and we could control the rotation by doing that. So, what else we have here? We have this is the shape of the pulse, 5 microseconds wide, repetition of 500 hertz, and we observed the onset of magnus by a distortion on this shape. Okay? So by measuring the initial distortion, could have the measurement of the threshold field, which would yield the line width of the magnus excited, as I mentioned there. And this is, as you people know, you are very familiar with that, this is the butterfly curve. This was measured for chromium and cadmium selenide at 4.2 Kelvin. Okay, this is a limiting field, HC. The left branch used in fact, use the branch that is for a magnum that propagates on 90 degrees with the static field. And the right branch uses that one that propagates at 0 degrees, and K equals 0. So measuring these numbers here, you have information on the line width, and measuring the H field, have a function of H field is a wave number, which is a function of H minus HC. And that's the way we measure the parameters. So these are several curves that we measure for the line width as a function of the wave vector. For different temperatures, we went up to 37.5. Beyond that, we could not observe anything significant. So, and also, we have those curves, and this was explained. I mean, this was analyzed. I mean, this was collaborative work with Sergio and Mauricio Domingues, and their analysis mostly, their objective was also to elucidate what was the mechanism that determined, that depends on line width and wave vector for a high and low K. By analysis on rate equations and identifying the coefficients of the rate equations, they showed that the linear region was due to 3 magnum relaxation, and the low K region was to decay into degenerate modes and subsequent 3 magnum relaxation. So this was the contribution of this work. And this went on to be published on the Journal of Applied Physics in 1984. This was a discussion of the paper. I just want to observe how this master dissertation I did. I mean, this was concluded in 1983, and I had to hurry. And I'm not sure, but I think my dissertation is the only. I mean, I think at the time we have typewritten texts, but all equations in my dissertation were made by hand. Okay, but they look pretty nice, I think. Okay, so. But I had to do it by hand because there was no time to do it in typewriting. I think, I'm not sure if that was the reason, if that was the way to do equations 40 years ago. I'm not sure. I think we did equations by typewriters. So, I just want to mention that, my training started with Professor Sergio, and I learned from him lots of basic concepts. One important concept was how to observe physical phenomena and try to exploit that for doing some engineering device, some instrumentation. And that's I always practiced in my career. Okay? A basic thing that I learned from the work with Sergio Rezende was always to observe if something. To observe the physical phenomenon and try to use that phenomenon to make a device. So, the same methods that were used to analyze, to analyze, a rate of population change of magnons or bosons or whatever, using rate equations, I still use. I don't work with magnetism at the moment, but I work with several phenomena in which I make devices, spectroscopy, reflectometry. We deal with the resonance concepts in engineering a lot, and we do that a lot. Just to show you that, I recently published a paper, which is an application in engineering, which is based, the model is based on rate equations. The same rate equations used to determine the relaxation mechanism. The relaxation mechanism in the magnum process in the master dissertation that I developed. So this partition, this modeling here using several couple rate equations to determine the rate of transport of molecular species in the oil through a gas phase So this is applied to measure dissolved gases in transformers, in high voltage transformers. By measuring those gases, you determine the possibility of malfunction of the equipment. So we developed the sensor, but also the modeling based on rate equation. Just published that paper recently, just to show that everything is all linked. Okay, all the basic equations are almost the same. Differential equations are similar in different parts of knowledge. So that's what I wanted to say. And I would like to conclude by saying that, sorry about that. Happy birthday to Sergio, and like to thank him for letting me be part of his journey. I mean, he's an example of integrity, ethics, and leadership, and is very inspiring for all of us. Thank you.
Thank you, Eduardo. Let's hear Eduardo again.
Remove here the.
Thank you, Eduardo. Let's move on to the next talk, which will be given by Professor Antônio Carlos Pavão, who is professor in the Fundamental Chemistry Department at UFPE. Professor Pavão works with computational quantum chemistry, superconductivity, magnetism, chemical carcinogenesis, chemistry of quarks, and resonance theory. Since 1995, Pavão is director of Espaço Ciência, the State of Pernambuco Museum of Science. Pavão is going to talk about molecular model for magnetic iron. Okay, Pavão, please, you may upload your presentation.
Okay, thank you, Antonio. Thank you, Fernando, and the organizing committee for this invitation. It's a great pleasure to participate of this memorable moment. Deixa eu preparar aqui minha apresentação. I'm sorry. I will also break this language symmetry, and I will speak in Portuguese.
Great, it's there.
Okay. I have selected 3 moments in the history to talk about Sergio. First, primeiro é time de futebol. Porque quando você olha para essa fotografia, você vê que todos são iguais. E o Sérgio trata as pessoas assim muito por igual. Não é em todos os momentos. Ele sabe, aí nessa foto a gente já tem isso expresso. E a capacidade do Sérgio formar um time, ele formou um time muito em Pernambuco, aqui no Brasil, né? E estou vendo no mundo também, claro. Então, ele tem essa característica de reunir as pessoas. E veja que ele está rindo. O Sérgio tem uma característica que ele dá risada, dá gargalhadas. Isso é uma coisa muito boa para a gente ouvir das pessoas, né? Do Sérgio. Então, isso é uma característica importante. Aí nós temos nessa foto aí, alguns estão se reconhecendo aí, o Maurício, que não está com a gente aqui agora, Silvio Canuto, mas os funcionários também, todos aí, é interessante destacar esse aspecto, a amizade que ele tinha com todos, e tem com todos. Outro aspecto também é esse político, né? Desde que eu conheci o Sérgio, eu percebi que ele tem uma posição e tem uma ideologia, porque quem tem ideologia não muda de posição com tanta facilidade. Então, Sérgio, a gente percebe essa coerência nas lutas pela defesa da universidade, pela defesa dos trabalhadores de um modo geral, né? Então, é um aspecto político que eu gostaria de destacar nessa trajetória do Sérgio. E também um aspecto que muita gente... Bom, todo mundo sabe que ele fez muita... O Lula falou, né? Quem viu naquela live da Academia Pernambucana de Ciências, o Lula falando do Sérgio, dizendo que foi o melhor ministro de Ciência e Tecnologia que o país já teve. Como se ele estivesse dizendo alguma novidade para nós, vamos dizer. Né? Nós sabemos disso. Mas ele também teve um destaque na divulgação científica. Esse é um aspecto que eu quero destacar aqui, porque foi no período que ele estava no Ministério, mesmo desde a FINEP já, é que ele, aqui no Brasil, nós tivemos vários editais de apoio à divulgação científica. Né? Aí é essa foto mostrando o Espaço Ciência recebendo o prêmio José Reis de Divulgação Científica do CNPq. E também o Sérgio teve um papel fundamental aqui no desenvolvimento, vamos dizer, na criação do Espaço Ciência. Porque o Espaço Ciência, quando ele assumiu a Secretaria de Ciência e Tecnologia, tinha sido recém-criado, e o que na secretaria dele logo virou uma diretoria, era um programa. Aí ganhou um status de diretoria, e depois nós crescemos, e hoje somos um museu de ciência que recebe, normalmente recebe mais de 100 mil visitantes por ano aqui, um orgulho de Pernambuco. Então, mas eu creio que a motivação do Fernando, da equipe, me convidar para a organização foi algum meu envolvimento. Eu já tive algum envolvimento, e tenho, com a questão do magnetismo. Então, em 89, nós publicamos esse trabalho aí, né, apresentando um modelo de cluster molecular para o ferro. Né? Nós fizemos para o ferro, mas depois fizemos também, está aqui, para o cobalto e para o níquel, estudando os 3 metais magnéticos da tabela periódica. Né? Então, qual é o problema que havia na época? Eu já vinha trabalhando há muito tempo, desde São Paulo, lá da USP, com o método do espalhamento múltiplo, que é uma alternativa que nós temos para tratar clusters. Ele é muito interessante, aquele modelo, porque você considera um potencial esférico simétrico em torno de cada átomo, e nos vazios que sobram, você considera um potencial constante, e casa as funções de onda de uma região para outra, enfim, dava um resultado bom. Mas quando você vai fazer, você sempre tinha um problema, que é os átomos da periferia, que chamados dangling bonds, esses orbitais que você fica sem saturação. E aí você injeta os elétrons que deveriam estar formando ligação, acaba entrando para dentro do cluster, e você acaba injetando elétrons para dentro do cluster. Além disso, quando você trata um cluster desse tamanho, você tem o grande problema de definir a multiplicidade de spin disso daí. Bom, aí, o que nós fizemos? Bom, então vamos calcular, e foi numa época que a gente já começava a utilizar, a fazer cálculos ab initio com mais facilidade, porque antigamente demorava muito tempo. Então, aí já foi possível, naquela época, calcular uma molécula de ferro 2 como sendo o cluster. Na verdade, é um limite, né? um extremo. Você considerar um cluster de 2 átomos. Mas qual é a vantagem? Que você automaticamente já resolve o problema do spin e dos dangling bonds, que não vai ter aqui. Muito bem, nós sabemos que no caso do ferro, na verdade, em cada centro atômico, não é dessa forma como às vezes a gente vê representado em livros e até em artigos, com um spin em cada centro. Não é um spin, são 2 spins. O spin total é 1. Então, isso nós sabemos. Então, aí a gente pode controlar a multiplicidade de spin numa molécula, um cluster de 2 átomos, uma molécula de ferro 2. E o que acontece? Quando você calcula a energia total dele, aqui são energia tipo Hartree-Fock, então você observa assim, que no caso do cobalto e do níquel, você obtém um quinteto realmente como o estado, o grounding state. É um quinteto, o grounding state. Mas o grounding state do ferro 2 é um septeto. Pode ver, a energia está mais baixa aqui. Não é um quinteto. E septeto significa o quê? Significa que em cada centro atômico você teria 3 spins, e não 2. Então, isso virou um problema. E daí? Então, quer dizer que esse cluster não pode ser usado? Foi daí que a gente falou assim, pode, vamos usar ele. Pronto. E fomos analisar esse sistema. Quando a gente analisou esse sistema, esse quinteto, o que aconteceu? Bem, primeiro, ele automaticamente já está satisfazendo aqui os 2 spins em cada centro. Spin total 1. Né? E depois, quando você vai comparar alguma largura de banda, desdobramento de spin, tudo isso dá muito bom. Coisas que no cálculo que eu fazia anteriormente, muita gente tinha feito com modelos de cluster, nunca tinha chegado a um resultado tão bom quanto esse aqui, de medir largura de banda, e demais, vamos dizer aqui, a gente poder identificar que é um sigma-U, que é o nível de Fermi. Quer dizer que são orbitais sigma antibonding, como é experimentalmente, se observa isso. Então, esse sistema é esse que é o estado fundamental do ferro 2, do ferro metálico. E automaticamente você vai explicar o 2.22 do magneton de Bohr dele. O que é? São os 2 spins, mais a polarização que vai acontecer tanto nos orbitais S quanto nos orbitais D. Isso é uma coisa que também nós analisamos. E o que tem de bronca aí? A diferença é que quando você vai analisar a distribuição de cargas que você calcula, os átomos de ferro vão ser diferentes do ponto de vista da carga. A carga elétrica, um vai ficar negativo, outro vai ficar positivo. Isso é uma coisa estranha. Como? Os átomos de ferro não são todos iguais, não é tudo neutro ali? Não. No cristal, eles têm ferro mais, ferro zero e ferro menos. Isso daí, quem já tinha dito isso era o Pauling. Vamos ver, eu fui pesquisar por que tem alguma. Como é que pode ter essas cargas positivas e negativas num cristal? Aí o Pauling tinha falado isso. Não, é porque, sabe por que é? Porque quem estabiliza o cristal, o metal, quem estabiliza é exatamente essa separação de cargas, a existência no metal de uma separação de cargas, que ele vai explicar como essa história da ressonância não sincronizada. Unsynchronized resonance. Porque nós conhecemos a synchronized resonance, que é aquela que acontece no benzeno, que se aprende na escola. Que é quando uma ligação vai para cá, a outra vem para cá, de forma sincronizada. Então, Pauling, usando dados experimentais, e ele pega o exemplo do lítio. Ele fala assim, no lítio, existe sim a ressonância sincronizada. Quando esta ligação vai para... Quando esta ligação vai para este átomo, esta outra ligação vem para este átomo, de tal forma que nós temos aqui uma ressonância desse estado para esse. Isso é ressonância sincronizada. Mas ele falou, não, mas existe a ressonância não sincronizada. O que é a não sincronizada? A não sincronizada é quando esta ligação vem para este átomo e essa outra ligação... Desculpa aqui. É quando esta ligação vem para este átomo e essa outra ligação não vem para este átomo. Então, neste caso, você recebe essa ligação, são 2 elétrons. O elétron que pertencia a esse lítio vai parar nesse lítio aqui. Quer dizer que esse lítio fica negativo. E esse outro lítio que perdeu fica positivo. Então, Pauling vai falar que é isso, ele vai calcular, usando dados experimentais, e vai perceber que realmente esse é uma energia que estabiliza o cristal. Todos os metais são assim, positivo, neutro e negativo. E aí, o que acontece? Ele tinha feito isso com dados experimentais. Nós, aqui em Recife, aliás, colaborando com o Rashid Mohalem, do Departamento de Física, lá da UFMG, né? E o Roy McQueen. O Roy McQueen, por que nós procuramos o Roy McQueen? Eu procurei também o Mohalem. O Mohalem tinha trabalhado com ele. Porque, para fazer essa conta que o Pauling propôs aqui, que é um sistema aqui do lítio, que eu vou ter 4 elétrons de valência aqui 8 elétrons de valência, desculpa, 8 elétrons de valência. Então, precisavam, para descrever esse estado, nós não poderíamos usar a teoria de orbitais moleculares, nós teríamos que usar a teoria de orbitais de valência, em que você poderia dar pesos para cada um dos estados aqui. E o único programa na época que fazia cálculo com 8 elétrons, com orbitais ortogonalizados, era o programa do Roy McQueen, lá na Itália, que na época ele estava na Itália. Aí, o Roy McQueen, com o trabalho, nós fizemos um cálculo e mostramos que o Pauling estava correto, realmente. E esse estado é o estado que estabiliza todo o metal. Então, e eu estou falando do McQueen, o Roy McQueen, para quem não sabe, eu estudei pelos livros dele, tudo aqui, depois ele esteve aqui em Recife, tem uma foto dele aqui, e então foi um grande trabalho que nós fizemos aqui, e que, para o Pauling, foi uma demonstração do que ele já tinha previsto. Lamentavelmente, nessa época, ele já tinha morrido. E depois, então, falando em ressonância não sincronizada, voltando aqui, então, como que se dá a transferência de elétron no cristal? Veja aqui, você tem uma ligação, essa ligação é transferida para esse outro átomo, este fica positivo, esse átomo fica positivo, e essa carga negativa que estava aqui vai se propagando no cristal. Quer dizer que a teoria da ressonância não sincronizada é uma teoria de transferência de elétron, é uma teoria. E aí, vamos estudar todos os fenômenos que tem, eu fiz várias aplicações, e inclusive algumas que vou mostrar aqui. Uma primeira, bom, vamos pegar nos cupratos e vamos tirar uma unidade que é semicondutora, o óxido de cobre, e vamos colocar um metal, sulfeto de níquel. O sulfeto de níquel é metal. Então, se você fizer essa troca, você vai aumentar o número de ressonância não sincronizada e vai aumentar, em princípio, a supercondutividade. Aí, esse trabalho aqui, nós mostramos, junto com o Albino, o Marcílio, o Marcos, várias pessoas aí, que a gente aumentou a temperatura desse supercondutor aí de 92 para 3 graus Kelvin, 92 para 95 Kelvin, e esse trabalho aí. E também aí vamos aplicar para outros, estudamos vários cupratos, né? E o que nós sempre percebíamos? Que as ressonâncias não sincronizadas apareciam. Por exemplo, vamos olhar nessa figura aqui do lado, eu tenho aqui o cuprato de lantânio e bário, então você tem aqui todos os sítios de oxigênio estão ocupados, está totalmente saturado. Agora, vamos fazer uma vacância, tirar este oxigênio daqui, que é exatamente que a gente vai ter o cuprato supercondutor, que a gente sabe disso, né? Tem que fazer as vacâncias. Então, quando a gente tira este oxigênio aqui, o resultado do cálculo mostra, tem que perceber direito, esse cobre aqui, ó, ele fica mais negativo, ele fica mais positivo, desculpe, ó, ele era preto, aqui, mais ou menos, tá? E ele fica aqui mais avermelhado, ele vai ganhando carga. Então, ele vai ficando positivo, quer dizer que ele vai perdendo elétrons e vai injetando elétrons nas camadas de CuO, que é onde se dá a supercondutividade, se dá nesses planos de CuO que tem aqui nos cupratos, que a gente já sabe disso também. Então, isso é interessante porque mostra que a supercondutividade tem a ver com ressonância não sincronizada. E tem a ver? Não, e na verdade ela é que vai, vamos dizer assim, explicar. Veja aqui os resultados dos cálculos que a gente fez. Quando a gente calcula o cluster inteiro, sem a vacância, o gap homolumo, a transição entre o último orbital ocupado para o primeiro desocupado, o delta homolumo, ele cai drasticamente quando a gente faz a vacância. E, observem, há uma concordância, uma boa concordância com os dados experimentais quando a gente pega o gap supercondutor. Bom, tem gente que não aceita direito, e não é tão simples, realmente há uma discussão, que o gap homolumo seria o gap supercondutor. Mas, pelo menos, tem que ter uma correlação aí, algum fator, mas que nós estamos na direção correta. Né? Quer dizer que essa teoria permite explicar, calcular o gap supercondutor, que é um dos grandes nós. Nós também estudamos, além dos cupratos, né, os pinictídeos e os supercondutores metálicos, né? Todos eles a gente encontrou ressonâncias não sincronizadas, né? E mais recentemente, isso aqui é um trabalho agora de 2019, a gente já vem estudando os fuleretos, né? Esses aqui do C60. Então, veja só o que acontece aqui. O fluoreto de sódio não é supercondutor, mas o de potássio tem 19K. Isso aqui faz 20 anos que já descobriram isso, né? E quando você tira o potássio, bota um átomo maior, a temperatura crítica aumenta. Então, há uma expansão da rede, isso é um negócio que foi descoberto. Então, como que você poderia fazer do sódio ser supercondutor? Bota um átomo de césio no meio, e de fato já vai para 10,5. E depois, eu estou falando aqui só para mostrando a figura, esclarecendo, os que estão em vermelho aqui estão em exposições octaédricas no cristal. E os amarelos, que são de tamanhos diferentes aqui, estão nas posições tetraédricas. Então, isso tudo tem importância onde colocar esses átomos. Mas, veja só, aqui o sódio já passou a ser supercondutor quando botou uma dopagem com césio. Agora, quando você pega esse daqui e faz a amoniação, você faz em torno de cada sódio, você bota 4 moléculas de amônio, a temperatura crítica triplica. Então, isso é uma coisa interessante. Então, nós estudamos, falamos assim, e vamos estudar outras moléculas que ninguém tinha estudado. E nossos cálculos mostraram que basta você hidrogenar o sódio, que você vai ter temperatura, você vai ter fluoretos de alta temperatura crítica. Isso daí nós fizemos os resultados. Isso aqui tem um artigo mais recente um pouco disso. O que a gente faz? A gente usa a teoria BCS aqui, só que aqui a interação elétron-fónon vezes a densidade de elétrons na superfície de Fermi, esse produto, a gente bota um ρ aqui e vamos parametrizar ele, mas com coisa que tem sentido. Por exemplo, eletronegatividade, a parâmetro de rede, e parâmetro de rede é esse daqui, eu estou dizendo aqui é o raio também da molécula que você está colocando, o delta homolumo, e com isso nós construímos uma curva aqui que, beleza, bate tudo com o experimental e prevê fluoretos de alta temperatura crítica. Muito bem, é isso que eu tinha que falar. Eu queria terminar aqui só mostrando essa escola de Atenas do Departamento de Física, que essa foto é muito conhecida, e que eu fui confundido. Uma vez o Sérgio apresentou essa foto, falou que esse aqui era eu, e eu sou muito parecido com esse aqui, mais bonito, mais parecido, e eu ficava orgulhoso das pessoas confundirem, falar assim, poxa vida, deixa eu estou lá, mas essa foto é de um ano antes de eu chegar aqui em Recife. Eu gostaria muito de estar nessa foto aqui. Então, eu me coloquei aqui, ó, vocês estão vendo aqui a minha cara, agora eu já faço parte, olhando, desconfiado, que talvez seja eu mesmo, mas parece que é o Albino, alguma coisa aí. E isso daí também é interessante, porque na Escola de Atenas original, do Rafael de Sanzio, ele se coloca no quadro, né? Vocês sabem disso, né? Sérgio Mascarenhas vai saber. Então, eu também me coloquei no quadro aí para fazer parte dessa história do Sérgio, que é uma história muito bonita e que merece todo o nosso respeito, admiração e inveja também. Então, muito obrigado por esta oportunidade.
Okay, let's cheer, Pavão. Thank you, Pavão.
Muito bom!
Okay, we have to move on to the next talk, which will be given by Professor Belita Coyle. Belita Coyle is professor in the Institute of Physics at the Federal University of Rio de Janeiro. She works in condensed matter physics. She's a theoretician, work with quantum phenomena of electron system, quantum devices. The title of her presentation is Spins in Semiconductors as Quantum Bits. Okay, Belita.
Antonio, she is also the director of the Physics Institute.
Oh, that's right. Yeah. She's also the director of the Institute of Physics. Thanks, Sergio.
Tá sem som. Impressão minha.
Belita? Okay. Is your microphone on?
No.
Belita, your microphone is off. We can't hear you.
É na barra de baixo, viu, Belita? Na barra de baixo. Tem um microfone na barra de baixo.
Fernando, você é do Mac Boy.
Puxa o cursor para baixo, aí aparece a barra. Baixa, abaixa mais. Para aparecer a barra.
Aí aparece o microfone aí. Não, mais para baixo, Belita.
Alexandre está dizendo que quem estiver controlando consegue ligar o microfone dela.
Padrão pode ligar, né?
Não. Padrão, você consegue ativar, padrão?
Belita, tenta puxar a barra branca a partir de baixo para cima, que deve aparecer o microfone.
No, I think you want to go back to Google Chrome and get into the window with the meeting, and that should allow you to start that on.
Yeah, go to Google Chrome. That then you do first the microphone, then the presentation.
Yes.
Just move the mouse a little bit in the lower part of the screen on the Chrome interface.
No. All right, go
down a little. Yeah, stop sharing, then make the microphone, then go back. Probably is better. Posso fazer isso aqui não, bicho?
A Belita, é na mesma barra que você põe apresentar agora. É na mesma barra. Só que no meio da barra.
É.
Onde você clica em Presentation Now, aí no meio da barra tem um microfone, aí você clica nele. Na parte de baixo, né? onde tem os 3 botõezinhos, né? Na parte de baixo, onde tem os 3 botõezinhos, e onde você aperta apresentar agora, aí você vai andando para o meio, tem a câmera e tem o microfone. Oi, oi.
Maybe.
Conseguiram.
Oba!
Agora você volta para outra.
Agora move o cursor para a direita e aperta apresentar agora.
Pronto, agora eu já sei. Sérgio, nos 100 anos, nos 90 anos, você usa o Zoom, tá? Que é melhor. Não veio meu seminário.
Tá ok. Só abrir agora.
Você tem que abrir a sua apresentação. Abre ela que ela aparece.
Mas está tudo preto.
Não, clica na sua apresentação que está embaixo.
Não está, não.
Ah, porque você fechou ela.
Deixa eu fazer uma coisa. Vou fechar isso aqui. Eu faço resumido quando for.
Se você descer com o mouse até embaixo, você vai ver os seus aplicativos. Aí você clica no que você quer. Vai descendo aí. Desça mais aí.
Não está, não está.
Ah, não, né?
Share screen. Eu tenho. Como é que. Cadê mesmo? Eu botei a tela inteira.
Alt Tab. Alt Tab.
Ah,
Pronto, isso. Agora.
Desculpa. Vou tentar falar rápido. Vocês querem que eu fale em português, não é?
You may speak in English.
Fala inglês.
Okay, because it's only in English, and I'm going to talk about work that's not exactly in magnetism, but from the talks I heard, I think it will fit more or less to what people are doing in magnetism. So, looking at the bottom of this slide, it occurred to me that since it's Sergio's birthday, this logo for the University of Pernambuco told me that the feeling, I'm sure, is going to be much. So I'll start for quantum computing. I started to be.
The microphone there.
Is it okay?
Yeah, now it's okay.
Bits, as you know, can be 0 or 1. Like the current goes through a transistor, You have one bit and it doesn't go with the other bit. If you do a combination of these two states with coefficients A and B, you get an error or a blue screen. This doesn't make sense for the classical bits. But for quantum bits, you can have state 0 or state 1 or any combination of these two states for complex coefficients A and B such that it's normalized. So this is superposition is a quantum property of the states, the basis state. So any two-level quantum system can play the role of a qubit. For example, this spin-and-a-half particle under a small magnetic field leads to two levels of the one spin up and one spin down. And you can take this as logical bit 1 and logical bit 0. And if you do a superposition like here in red, it's okay and it's a perfectly acceptable qubit state. So the 1 and 2 here form the basis of a Hilbert space where the qubits live. The restriction a squared plus b squared equal 1 allows you to choose A and B like I show here with angles theta and phi. And these are the spin rotations in the Bloch sphere that was mentioned earlier. So you can perform any rotation of the qubits changing theta and phi. Now I'm talking about real space. Let's see how this connects to real space in the lab. There's a theorem for this particular problem that all one qubit operations and only two qubit operations will lead you to a universal quantum computer. Which means you can perform any operation in a quantum computer by combining one qubit rotations with two qubit coupling. So since spin is a quantum attribute, there was a proposal of Kane in '98 to use donors in silicon that have an electron, donor of one electron, simple donors, as a qubit to use phosphorus spin, electron spin. So what's phosphorus doped silicon? You look at the chemistry here. Silicon is a group 4 element. So it has less shell is 3s2 to 3p2. And phosphorus is next to it in the group 5. So it's the same structure, but only one electron more and also one proton more because phosphorus is one proton higher than silicon. So we can interpret this information to saying that phosphorus substituting one silicon atom in silicon, in the crystal, will give you back silicon if you take out the electron and the proton, and this is a hydrogenic atom. So you can think of phosphorus doped silicon as bulk silicon with one extra hydrogen atom. And the two qubit operations for this, we can perform spin operations by rotating the spin, and the spin coupling can be of like the polar, but dipolar is too small. It was mentioned earlier, the types of coupling between spins. And because the dipolar coupling is weaker, this implies long operation times and it would not be enough to keep the coherence of the qubits. Now we can think of exchange, and we'll discuss it in the next slide. So the hydrogen atom has one bound electron, and donors in semiconductors have one bound electron also, the type we're talking about. But gallium arsenide has nuclear spins, and nuclear spins are the main source of electron spin decoherence. So dipolar and gallium arsenide won't do it. But silicon holds long spin coherence times because the major percentage of silicon, natural silicon, is silicon-28, which has 0 nuclear spin. And it's possible to isotopically enrich it so that you have 100% silicon-28 And this will give you very long coherence times. And silicon, moreover, it allows integration with current electronics and technology. This system, phosphorus doped silicon, is N-type silicon. It's very well studied, very well known, very well processed technologically. So it would use the know-how in processing doping silicon to build this hypothetical quantum computer. So let's talk about the two-spin entanglement. The idea then is to think of the donor pair in silicon as an H2 molecule. So I'll just remind you how to calculate the exchange. Here are the indicated nuclei A and B, electrons 1 and 2, and this is the H2 molecule. We assume the nuclei are fixed because this will represent silicon sites in the lattice. And the distance is big R. For the charge, for the electric interaction between electrons and nuclei, it's very easy to write the Hamiltonian for the charge degrees of freedom. Is the kinetic energy of the electrons plus the sum of the Coulomb repulsion between all pairs of particles. So if it's A, B, or 1, 2, same charge, you get sign plus here. And if different signs, it's sign minus. So you have the exact Hamiltonian for the charge. But I'll show you why the spin Hamiltonian can be thought of the equivalent to the charge Hamiltonian. The effective Hamiltonian for the Coulomb part or charge part can be written as this effective spin Hamiltonian because they have, you can choose J so that the ground state manifold is exactly the same as the charge Hamiltonian. So you have a triplet and a singlet as the lowest levels, and you can show if J is chosen equal or proportional, it's a question of definition, to the difference in energy between the triplet and the singlet, you have the same spectrum for both Hamiltonians, and this is how you get the exchange coupling. I show this because I want to do the same with phosphorus donors in silicon. So let's see. This is the original proposal by Bruce Kane in a Nature 1998. And as I said, he considered phosphorus pair in silicon like the H2 molecule. And he used the expression here, J of R is R to the 5 halves, and exponential of the R. So J depends on the distance between the donors as a power and an exponential. And this is what's plotted here on the right. This plot for J of R as a function of distance R of order of hundreds of angstroms. So this is the H2 molecule expression, and this expression is valid for R much larger than the Bohr radius. This is the Bohr radius. And the Bohr radius is very big, and the expression is for R much larger than the Bohr radius. And the Bohr radius is so large as compared to hydrogen because of screening the electric constant of the medium, and because the effective mass of the electron in silicon is smaller than the electron mass. So this is the proposal by Bruce Kane. You have an array of phosphorus donors in bulk silicon and an insulator on top, and then gates, so-called A gates and J gates. Because the exchange, the constant J is proportional to the overlap between the wave function of the two donors in the case. The exchange coupling will be zero if you put a repulsive potential in the J gate, so the electrons will be apart and the overlap goes to zero. So in this case, J equals 0. But in the lower case, you turn on the J gate to have an attraction of the electrons, and the electrons increase the overlap, shown here in the bottom left, and you have J different from 0. So you can manipulate and control the coupling between the electrons, the two qubits gate, just by changing the J gate potential. Now, is it valid to use the hydrogenic model for silicon. A hydrogen molecule in vacuum is very different from silicon holding a phosphorus donor. So this analogy is not allowed. And we must use the silicon electronic structure coupled to the hydrogenic model to find the wave function of the phosphorus in silicon. And actually, there's a strange effect because the bound electron ground state in silicon is given by this oscillatory distribution, which is not commensurate to the lattice. And the reason for these oscillations is the interference between the Bloch states at the bottom of the 6 degenerate band minima in silicon. Silicon has a funny band structure that is 6-fold degenerate for the conduction band, and the Bloch states for all these states contribute. The plane wave part of the Bloch functions have a e to the ikr with different k's. There are 6 k's each one for one minimum, and then when they this part 6 of the wave Bloch free electrons function, the plane wave parts, they interfere and they result in this very interesting pattern. And you see the central part where the donor is larger. This is because the k vectors, if you sum the 6 plane waves, the maximum of the sum is happening for k equals 0 for all of them, for r equals 0. And then the wave function and the Bloch functions are pinned to the phosphorus donors. It's important to know that because if you remember that the exchange coupling is proportional to the overlap, if you have a second bound electron like this one, it will have the same distribution around it. So if you have 2 of these figures, the overlap will be oscillatory, representing the oscillations in the wave function. So if you calculate the exchange coupling for this wave function, you get a strongly oscillatory behavior for the exchange coupling and very anisotropic. So if you go along the cube aresta, then if you look at the lattice point, silicon is the red with green. I'll show you about the germanium. It goes very smoothly, and this would be acceptable for exchange gate. But in the if 110 and 111 directions, it's highly oscillatory. So as I said, if you can place 2 donors exactly at the 100 direction, the exchange will behave similar to what Bruce Kane expected. But displacements of the pair relative position on the order of atomic neighbor distance leads to a sharp variation in J of R, typically suppression. So if you go in any of the other in any direction that has a Z component difference from for one and the other, then J will vary by orders of magnitude. So it's important if you want to use the exchange gates as proposed by Kane to place the donors exactly along the 100 axis, which is hard for the current status of fabrication of the samples. The best possible accuracy for phosphorus atoms in silicon is around 1 nanometer or a couple of nanometers. So you cannot have the precision to place 2 donors at 200 angstroms apart in exactly in the same crystal axis. So this is a fabrication challenge. It's hard to place the donors in the same place. So how to overcome the oscillatory behavior in silicon? The first proposal to overcome this possibility was I was involved. And what to do is to observe that silicon has a cubic symmetry, FCC symmetry. And the reason for the 6-fold degeneracy is the symmetry of the crystal. But if you lower the symmetry, then you should lift the degeneracy. And indeed, if you apply strain along the z-axis, if you place the donors anywhere in the xy plane, in the same xy plane, you don't have these oscillations anymore. It's very much like the hydrogen atom. But if one of the positions has a z-axis direction, the direction of the strain, then you recover the oscillation still stronger. So it partially solves the problem, but I heard from the growers that it's not easy to place two donors in the same Z plane. And I should say also that these studies motivated people to work hard with silicon doping. And although it didn't reach still the stage of building a quantum computer, it had an impact in the silicon industry, the fabrication of usual devices. And the interest still is on how to overcome the oscillatory behavior in silicon. And I found this paper, number 2, that was submitted to FRL. It's from the archive 2020, this year, August this year. And it mentions here that with this radio blockade entangling gates, he can solve the current entangling gate implementation rely in highly challenging precision donor placement and substantial gate tuning to achieve what's needed. So until today, there is a strong interest in making this work somehow, because all other aspects are very well studied, very well known. The 1 qubit operations are rotations of the spin around the nucleus. And for this paper that I read, I try to show here on the bottom right corner the figure of the paper. It doesn't show very well. It's a very complicated scheme with lasers and gates, and I think it's not feasible in practice. And he also assumes that the two donors are in the same plane, XY. And I think it will be the same problem as the strain. So this is an open problem, and that's why silicon quantum computer didn't go very far. Now people are doing in silicon quantum dots, electrostatic quantum dots. But this is also a problem because each quantum dot will have a different shape, a different spectrum, and phosphorus in silicon guarantees identical qubits potential. So then you need to characterize the double dot. But silicon communities turning towards that, and they have more optimistic results now. So I now go to further work that was done. I won't talk about each of them individually, but the original motivation for working quantum computer from Feynman is simulating the dynamics of a quantum system. And we studied the Hubbard model with the silicon with phosphorus chains, as indicated here. And we show that it is a valuable system to implement this model, Hubbard model. We include disorder like errors in the placement of the qubits, and we show that it still keeps some correlation in spin-spin correlation function. Then we also studied transport along atomically placed phosphorus ribbons in silicon. This is a more recent study. And from the fabrication side, the fabrication of these wires is very advanced. You see here pictures of and the Ohm's law here. So these chains are being considered as contacts for nano devices. And this progress is enormous. So thank you for your attention. I'm sorry, I think I'm doing this time, so I have time for a few comments.
Okay, thank you, Belita.
I have a few comments on Sergio.
Okay, go ahead.
Because do I have time or?
Yes, go ahead.
My professor in basic courses, he was my professor, and it was interesting to see the human side of Sergio. Is that one class he showed music with a laser. I don't know if the mechanism was the laser music player, but and then he showed this and showed many things after that in the basic electromagnetism course. And at the end of the class, we said, we're going out. No, you all stay, please, you all stay. And he turned on the demonstration of the music of the lady. And then he said, I wanted the class to finish with music. So that was very inspiring, that you don't need to be a cold person to be a good scientist. So he was also my advisor when I was going abroad for Berkeley. Actually, he advised me to do that. And he went to bring my application in hand. At that time, there was no internet. Everything was on paper in an envelope. And the post office, as today, was not reliable. So it was good to have someone to take your application to the office. And he came to give my application. And the person asked him, are you applying for graduate or undergraduate? Você está aplicando para graduação ou pós-graduação? So he always looked so young in his career. He did a great job in physics, in politics, and personal skills. And he's now 80 years old. So I saw this picture in Erasmus presentation, and Erasmus. If you look at Sergio was my teacher, you can see here. So at one point, I was younger than Sergio. There was a good crossover. So thank you, Sergio, for your attention. And
okay, let's hear Belita, please. Okay, the last talk for this part of scientific presentations will be given by Professor Nissim Zaguri, who is also professor in the Institute of Physics at the Federal University of Rio. Professor Zaguri works with elementary particle phenomenology, magnetism, statistical physics, quantum optics, and quantum information. He is going to talk about reminiscence of an old collaboration with Sergio Rezende. Professor Nissim, please.
Okay. Just a minute. Let me find my talk.
Sid, your microphone is on.
Hello. It's on?
It's not appearing yet. It's not yet appearing.
The
sound is great.
Just a moment. Okay. You are hearing me, seeing me?
Yes. Yes. But not the presentation.
Well, I should have put that. Oh, okay. I guess I can't find it. Well, it's aqui eu apliquei. Oh my goodness.
Where's the Mac boy? Fernando, socorro, Fernando.
Well, showing me that.
Nós podemos ver você sem problema. Sua janela está aberta. Tem que abrir a apresentação, né? O PowerPoint, né?
Ué, onde é que eu abro a apresentação? Detalhes da reunião?
Não. Você vai lá embaixo. Você abriu uma janela ou a janela inteira? Quando foi apresentar?
Ah. Eu estou apresentando, mas
mas quando você entrou, você escolheu apresentar a janela inteira ou só uma janela?
Eu não escolhi nada.
Então você sai para a apresentação. Deixa eu lhe mostrar como é. Para a apresentação.
Parar a apresentação, parei.
Pronto. Aí você vai no canto inferior direito. Tem três.
Apresentar agora.
Exatamente. Aí você escolhe
a tela inteira.
Mas é importante ter sua apresentação minimizada para você.
Pronto. Agora você abre a sua apresentação.
Agora eu posso apresentar.
Isso.
Ok, agora estão vendo?
Sim.
Yes.
Mas eu não botei a tela inteira aqui.
Maximiza aí.
Ok. Ok. Em inglês. It's in English, né?
It's better to be
Ok, sim.
Ok. Well, I first met Sergio socially when he was a student at MIT. At that time, I was a postdoc in Harvard, and we met socially. And after that, Sergio returns to the Catholic University. He finished his PhD, I guess, in 1967. And he returns to the Catholic University. And I was working there since 1967, since August 1967, yes. And Serge was working in magnetism. And I was working particle physics at that moment. And I was curious about the work of Serge and see that he was dealing with, I guess at that time, on the problems of what happened with magnetoelastic waves when you change the magnetic fields. And then I thought, well, there should be some quantum effects there. And I started to discuss with him how you could calculate those processes using quantum mechanics. And that then gave origin to a few papers that I guess I'm going to review them here because I think that it helped a lot for several papers that followed this one that I didn't participate, but Serge did. Well, the first thing that we discussed and published 2 papers about it, it was what kind of states should be the states that we should use when we want to make a macroscopic, when we want to pass from the quantum mechanics case to the classical mechanics case. And one thing first that I observed to Serge, that we could not use the quantum number states of Magnus, but we should use coherent states, because coherent states, I knew from quantum optics that were the best states that we could use that could reproduce the classical observations, and at the same time, the coherence on classical observation, and also the states such that when you make the average of the physical quantities would reproduce observable results. And then Sergio presented me what was the energy that was used when you describe the Magnum states. And where you have the integral of the density of the, here the mz and m. mz is the magnetization along the zx, where where zx is the x where you apply the external field H. And you have another contribution from the polar field was the proportional to the magnetizations of the transverse magnetization that here is defined by this M here. And the x-axis, I'm sorry, this is for the exchange energy and this for the dipolar fields. And we showed then that we could reproduce these equations as long as we took coherent states. But we could not reproduce them if you take Fock states, because then the average of M, it would be 0. And we were able to reproduce the energy and the momentum, the momentum of the states in this form. So, and that was our first paper. Then we discussed also, applying these ideas, we discussed what would happen with the ferromagnetic magnons when you change suddenly the magnetic field. And then we proved that first the CK here are the Magnum creation and annihilation operators. And we showed that they are related in the situations from that depend on the time that they find them. And for a given, that depend explicitly in the time, not implicitly, but explicitly in the time through the magnetization field from the magnetic field. And the relation between two times is given by these equations, where this is an equation operator for a higher magnetic field, and these are for a lower magnetic field. And this gamma k, it's is this formula here, where the Ek and Ek prime, K prime, are the ellipticities of the spin waves for one time of the magnetic field, and here for a higher magnetic field. We showed then that the ground states are related by this formula, and the final states, if you start with a given nk state, you have the final state that's given by this formula here, which shows that besides having a term here that corresponds to a magnum with any magnons at the higher field, you have magnons with other, and here it's should we have a minus sign, magnons from the traveling in the direction k, in the direction minus k time in the high after t greater than zero, where zero is the time where you change the magnetic field. So there is, besides this part here that corresponds the classical result, there is a creation of pairs of magnons that is a pure quantum result that is due to the fluctuation of the vacuum. Well, after these papers, we decided to write a more general paper. I forgot to tell you that, but I will tell you, this corresponds to the first paper. The second paper, which is about the excitation of coherent magnetic states, I'm going to talk about in the when I talk about this third paper that describes a theory of microscopic excitation of magnons. That is, we started putting here everything that we knew about it. So we start with the Hamiltonian, where you have the coupling of the magnetic moment of the electrons. Here we are talking about the magnons on insulating ferromagnetics systems. Then we have this coupling of the regular coupling of the magnetic field with the spins of the electrons, and then the exchange between the spins of the side psi and j, and then the dipolar interaction between the side psi and j. So to try to diagonalize the Hamiltonian, we starting by using the Hossen-Primakov approximation, where we write down the spins, the localized spins, as assuming that there is the spin in the z direction. It's S minus A dagger A, and assuming that A dagger A will be a small contribution, so that we don't produce spins less than minus S, components of spins minus S, and write the spin creation operator like that, and the spin annihilation operator like that. These are rather angular momentum operators. So neglecting then products of three or more operators, magnon operators, we obtain this Hamiltonian, which should be valued as long as the average value of a dagger AI is small, which it is for small deviations, and where this RAJ are given by that. You'll see that there is a delta J here, so this corresponds to same operators here, and another term that comes from the exchange and dipolar interaction that should be calculated, assuming that you have next neighbors only. And here, Sij comes from the dipolar, part of the dipolar term, when I and J are different. So this is the Hamiltonian that we will start with. And then we do a second transformation. We use the Bogolyov-Dyablikov transformation, where you expand the annihilation operator of the localized magnum through a Fourier series of where should appear the annihilation and creation operator of the magnum, so we will be able to diagonalize. And solving for the psi and psi star, we finally find the Hamiltonian that takes this diagonal form. And for example, if the applied field is uniform, this is very simple. It's psi I is square root 1 of square root of n u e to the I k r. And here appear, notes that appear here, psi star. So in this is a summation k, so I could have written this as psi minus k, psi dagger minus k. So it shows that that momentum is conserved. And uk and vk are given by that, as it happens in all Bogolyov transformations. So the commutation relation between the annihilation operators and creation operators are preserved. Ck, comma, C dagger k is delta de kk prime. Then I just repeat, and this mu k is given by this formula here, where bk and ak are these results for the cubic clots. So here you see this d is related to the exchange constant. M appear here, the saturated magnetization. Theta k is the angle between the z-axis, let's say the x-axis, and phi k is the azimuthal angle. And from these relations, so we can find that the ek, which is we call h omega k, is the frequency of the oscillation of the magnum wave. It's given by this relation here. So with that, we have now Hamiltonian that's completely diagonalized. And we can now to try to see how one able to excite states. We first notice that the Fock states are given by this formula here, and they have no average over the transverse magnetization, as we said before. The coherent states that are a combination of the diagonal states have a finite average value of the transverse magnetization, and we can show that magnetization is then given by this formula, which shows that the magnetization, the X and Y is given by that, shows that the magnetization then describe a ellipse in the transverse plane. So this this dipole is responsible by the ellipticity to be different from zero, from different from one, as in the figures that have been shown on the propagation of the spin waves. So in this, so in the microscopic case, you see then that the propagation of the in the direction, in a given direction, transverse or not, but the transverse magnetization is given by always by this formula here. Bon. Then in this paper, we describe how we could excite the magnons. Well, the first we discuss how to linear excite the magnons. This can be done by a transverse field turned on at t equals 0. Let's say we have this formula, and then we have to add in the Hamiltonian, besides the Hamiltonian H0, you have an Hamiltonian that will be described by this Hamiltonian here. You have decoupling between the phonons, the electromagnetic fields, the magnetic field oscillating coupled to the magnetic moment of the electrons are given by this equation, where GK it's a kind of Fourier transform of the operator, the extra operator that is transverse, that's described by this small h here. So this gives rise to a time evolution operator that can be expressed like that, and I find if the initial state is the vacuum, you have a final state that's a product of coherent states of that form, where gamma t is proportional to this kind of Fourier transform of the field H. Another kind of way to excite these magnons is by a parametric excitation of magnons, where the Hamiltonian that describes this excitation is given by this pair. Here you see that you create pair of magnons with different opposites. Okay, this K here should be a vector K. K vector minus K vector in all directions. And the whole K depends on the direction through this theta K and phi K. For example, if you see that theta is equal 0 and the excitation is parallel to the static field, then there is no propagation in the direction of the static field. And if the excitation is perpendicular to the field, then you have propagation in the direction of the static field. You have no propagation also around the static field, also and full propagation in and here full propagation in the transverse direction. These were the papers that we have worked with at that time. And when I started to do this talk, the first thing, well, I should try to see what's new about this this field, because I have not been working since Sergio left Rio de Janeiro in the 70s. I have done one or two more papers with some students. But then after that, I just changed the subject and I never did more work until I was invited for this paper. Then I started to see what I could talk. And I was surprised to see how many new papers are on this subject nowadays and how interesting they are. And among these papers, I see a lot of papers written by Sergio, and some of them that caught my attention was the theory of coherence Bose-Einstein condensation, that and these two papers that I try to read and try to understand, and I saw really they are very, very, very good papers and very impressive, because I saw that how Sergio was able to explain all these experimental results on at that time through using the same kind of approximations that we are considering when we wrote this paper, but at the same time taking account dissipations in different times, and then showing that how the evolution of the system being driven by a squeezing state had evolved, changing, and see what kind of parts of the Hamiltonian should be important to describe each part of the evolution. Here is a complicated situation where we have a driving field, a squeezed driving field that produce pairs of magnons in the system, but they are able to drive the system to a kind of boson state through not directly going to the time equals zero, but changing the changing, I forgot it's missing the term now. Well, it's changing from the Bose-Einstein condensation to a situation where you have the Bose, I'm sorry, a thermal Bose distribution to Bose-Einstein condensation, and using not only the terms, this Hamiltonian that described, but take in consideration all four magnum terms in the Hamiltonian, and take in consideration also the different relaxation times of the cavity and the magnums and and in the situation where you have first have these hot magnums gas to the situation where you finally get this Bose-Einstein. This actually, and so that another thing that has impressed me, it's as I said, is that there's so many new papers about the subject with very modern applications. Indeed, the one last paper that I saw that was impressed with me, it was John Applied Physics letters that I saw by Agarwal, where he showed that there is entanglement. You can construct entanglement inside a cavity with two Yagi spheres by pumping the cavity with a squeezed state, so that you create entanglement between the two spheres, macroscopic entanglement between the two spheres. That showed how these new developments can be important for information theory. So it's surprising me. Well, finally, I just want to congratulate Sergio for his brilliant career during these years, and I hope that we will be able to commemorate I hope that I'll be there to commemorate the 19th anniversary. I guess he still have a lot of things to do, and it will be very nice to see what's going to happen during these next 10 years of work. Well, congratulations, and thank you very much for
okay. Okay, let's thank you, Professor Nissim, for the presentation. And with this, we finish the scientific part. And now Professor Cid comes back to the closing ceremony. Thank you.
Okay, we are arriving at the end of our symposium. But before closing, we have three people who will give some message to Sergio. The first one will be José Rios. He will speak in about 5 minutes. After him, I will read a message from Sergio Mascarenhas. That's a short message that it will take about 2 minutes. And after that, Fernando Machado will read some message from people in the magnetism area. And we will give some news about future in magnetism of Sergio. Okay, so I invite Rios to start his talk. I think that he's trying to connect now. I don't know. Nissim still.
Sid,
I try to finish.
Can I have a quick word?
Papai, se você fechar o keynote, vai dar certo.
It's okay. I have to close the keynote.
Sidney Fernando, I'd like to have just a quick statement.
Yes.
I just forgot, I apologize. I forgot to thank the invitation for this event. I just passed that one. I'm sorry. But I feel honored for being invited for this. That's what I wanted to say. Thank you.
Thank you for your participation. Oh, okay, now I think that Rios may connect his computer.
Okay, no view graphs, no equations. Can you hear me?
Professor Nissim. Oh,
yes.
I you hear me? If
yes.
Yes.
I have no view graphs to show. Should I speak Portuguese or English? Sergio.
English, please. English, please. So that our friends from abroad can understand.
Today, more than any day, you order. English, I will do. Okay. I was to make a brief parkour trajectory of what Sergio Rezende means to all of us here in the University in Pernambuco, and why not all of us in physics and science in Brazil. Her Excellency, the Minister of Science and Technology. Can you hear me, Sergio?
It has a microphone on. I think that Belita.
Belita, por favor.
Open. Belita, please close your. Okay.
His mic open
okay.
Also. Can you hear me now? I will hold this here. So, 80 years is quite some time. Remarkable. And I was thinking how to put in perspective your contribution, because everybody has made so many detailed analysis of your work, of your contributions. What's left for me is, in brief words, try to make the frame where we're going to fit on ours today. And what is this frame? This frame is science along history until 80 years means that when you were born, it was a few years next to Néel and Bloch creating the magnetic waves and creating the discovery of high ferromagnetism. I'm saying is things that I was looking about to your trajectory. So we go back 80 years and go to 1940.
Seu microfone está aberto, Cid.
Okay, I did a step of 80 years. Sergio Rezende, born. Magnons as waves of magnetism to explain relaxation, first given a few anti-ferromagnetism too. Then we go back 80 years, which is twice your age. Whom we meet in science, Maxwell papers. Another 80 years. Who is there? The guys who are beginning electricity, Coulomb. I will not go further back because I have no time according to me, and I know that you are all tired, but each unit of 80 years, if we go 6 units like this, we come to the Europeans arriving in South America. But we also can move backward to the future. And let's move up. Instead of talking about 1500 when Brazil was arrived to by the Portuguese, no science, no idea of making science. Then the Dutch, the Holland people came to Pernambuco and tried to install some science. They even tried to install some printing, never worked. It was forbidden. And we keep moving back to today, and what we have. After that, another 80 years, and we Brazil coming to colony without whatever as university you can mention, not possibility, forbidden to print books. 1808, when Napoleon invaded Portugal and made the people come to here. And then I am coming back now, I'm going to touch the time of Marxists again, and my way back has to do with a very important thing. I'm trying to reframe. Can you see this? The origin of species. And I am about to finish, Sid. How many minutes I have? I'm coming back to 2020. When this guy was writing this, Brazil had a comment by this fellow saying that he was ashamed of coming here because he never wished to put foot again in a place where there was. That's what he saw here. And he mentioned this about Pernambuco. Unfortunately, we have good and bad things, as everywhere. As we move further, we get to 1820, around the time where people discovered the spin. The spin exists 20 years before Sergio Rezende was born. Before that, nobody would talk about spin other than spinning around. But spin, as you all talk today, was discovered 20 years before Sergio Rezende was born. So he's on the subject. We move again, and I should mention that by the time he was born, it was 1940. 6 years later, University Federal Pernambuco was founded. So we have the same age, Rezende, the university, etc. So it's a very young place to do something he is doing as an example in a magnificent way. We are trying to establish a contribution in our society in terms of doing science as a piece of important things to be do in civilization. Just to finish, I'm going to read the counter cover of this book in a by some guy of Nature. He says the following. He said that the origin, and when he says the origin, he uses the book by Charles Darwin. The origin is one of the most important books ever published. And the knowledge of it should be a part of the intellectual equipment of ever-educated people. The book will endure in future ages as knowledge of science persists among mankind. We are seeing now, Western side of the world, two countries doing things totally against this kind of viewpoint. And Sergio has a presence in this fight for the advancement of knowledge for the good of mankind. I have no doubt. So I'm going to read again in a different way, last sentence. Instead of reading, this book will endure in the future ages, I am going to read this, which his example will endure in future ages so long as knowledge of science persists among mankind. Thank you, Sergio.
Well, now we have to switch to Portuguese because I received a message from Sergio Mascarenhas, a message written in Portuguese to Sergio. So I have to read this message. It will take maybe 2 minutes. Querido Sérgio Rezende, você para mim é modelo de tantas virtudes e qualidades, tanto científicas e acadêmicas, mas ainda mais importante destas do lado humanístico de sua personalidade. Quando te encontrei, rápido reconheci como você é e me apaixonei por você, pois você é autêntico, outra rara qualidade. Quando, há décadas, no CNPq, sonhei e lutei por um programa de centros emergentes para o Brasil, tão necessitado de se libertar dessa herança de 500 anos sem educação, ciência, tecnologia e inovação, depósito vergonhoso de escravos negros, sempre pensei que aquelas áreas seriam o caminho real para a nossa libertação. Quando foi possível trazer essa ação para o Nordeste, de onde migraram Schemberg, Leite Lopes, pensei em você para a luta e o verdadeiro milagre ocorreu. Também pelos jovens que aqui estavam, hoje maduros cientistas. Hoje também comemoramos esse seu legado. Parabéns, Sérgio Rezende. Bem, a partir de agora, então, from now on, Fernando will read some messages that he received from different people, and I think that he is going to make some announcements after that. So, Fernando, please. Okay, Fernando.
Okay, 1 second. I'm going to put some slide here and present now. Ok.
Você é o único que não pode errar nesse negócio aí.
Não, posso não.
Que não tem direito de errar.
Não, já. Ok, I'm presenting. And let me open. Okay, can you see, right? Can you see?
Estamos vendo.
Okay. Albert Fert, that was a Nobel Prize in 2007, he asked me to read this message to you. Arthur said, I'm going to send his email so he can keep with your records. So he said that he wished you the best in your anniversary, that he admired you for your contributions to physics, and he wants to thank you for what you brought and what continue to bring to science. And he also mentioned that he admired you for what you have done for science in Brazil. It's amazing, incredible. So he hoped to meet you soon and talk with you. So Albert Fert. So that's the message that he asked me to read to you. And there is one announcement that I made a slide, but I'm going to stop here because I guess Marcelo Nobel is at the room.
Yes.
So let me close here and ask to Marcelo, please.
Hi. Well, it's a pleasure to be here among so many good friends. Sergio, congratulations. Happy anniversary and health. That is more important than anything else. It's a pleasure to be here. And I would like to announce just today, we received the green light to publish a special issue for the Journal of Magnetism and Magnetic Materials in honor of Sergio Rezende, from basic magnetism to magnonics. So the the friends from Sergio sent the proposal few days ago, and we managed to make a speed approval in order to announce today. So thank you very much. It will be a pleasure to receive your contributions and have a special issue of Journal of Magnetism and Magnetic Materials in your honor. Thank you very much, and congratulations.
Okay, I will go back to my short. Actually, this is the email that was sent by FET. I'm going to deliver to Sergio. And I had made this slide because I didn't know that Marcel was able to make. He had some meeting before this the closing ceremony. But one thing that I like to record here, like diamonds are forever, so a special issue at the Journal of Magnetism Materials are also forever. So we hope that you will enjoy this gift that was proposed by the organized committee, and that was announced by Marcelo. And we thank him for being really, for carrying this in a short time and being so helpful. He actually was very important in get things run quick. So I also like to wish you the best and congratulate you for your achievement. And thank you for your teaching. I start with you as a scientific initiation student, and I'm still doing that. I'm still learning. And I like to thank you for your friendship along these past 43 years already. So long life, Sergio. Thank you very much.
Fernando, I think that now we open the word for Sergio. Maybe he wants to say something for us.
That's the grand finale. The grand finale. Something.
Okay.
Wow, it's not easy to speak after almost 7 hours with an interruption that we had in the beginning. I'm really very touched and very thankful to all of you. And I'm sorry for our European colleagues. It's almost midnight, or perhaps it's already midnight in Kaiserslautern. So I'm really touched. And since I knew it would be difficult to speak, I decided to prepare some slides. And I hope you allow me to show some slides. 15 minutes, I'll show the slides quickly. Can you see this slide?
Yes.
Yes.
Yes, but you have to put.
Yeah, here.
Okay, now.
Ok, aos meus amigos, colegas brasileiros, muito obrigado a todos vocês. To all of you, I really thank you a lot. Burker, danke. Manuel, Roberto, Padrón, muchas gracias. Dino Fiorani, grazie mille. My first thanks go to the organizers. You see, until 1 week ago, I had no idea of what they had prepared. And in fact, I learned about the international reaching of this workshop by a message that I received from Berkeley, because I sent him a message about physics. And then he said, I'll see you on October 16. And then I learned that there will be people from abroad. So I to the organizing committee, to the chair, Cida Araújo, Antônio Azevedo, Eduardo Padrão, Fernando Machado, and Flávio Menezes that I haven't seen here. And I'm also thankful to magnetism. And magnetism, a very important field of physics, but it also attracts people. We are here today, tonight, because of magnetism. And I'm thankful to magnetism. I also thank this terrible virus, because if it were not for the virus, we would not be here. There would be no celebration. See, for a celebration like this, having foreign participants, visitors, we would have to have money to pay their travel and their expenses, and Brazilian science is broken. We have a government that doesn't believe in science. They don't support science. Fortunately, the scientific community is reacting and resisting. But if it were not for this terrible virus, we would not be here. And I also thank Elsa and Leo, my parents, both deceased. Here is a photo of Elsa and Leo in Rio de Janeiro. In the year they got married. This was 1937. And 4 years later, there was a future scientist. They never imagined that they were putting in this earth a scientist. Now, time went by, and there I was in 1966, at MIT, with my colleague, David Bullock, fixing a power supply for a magnet. That's how a power supply looked like at that time. It had no transistor. It only had tubes. And in fact, it was easier to fix because usually the problem was with a vacuum tube. We found the problems and we fixed. And we had several of these power supplies in the lab. And then I came to Brazil, as was already mentioned. And in 1969, I was in the first Brazilian symposium in solid-state physics, organized by Sergio Mascarenhas. Fernando just read a note from Mascarenhas. Mascarenhas was an inspired. He's 92 years old now, so he's 12 years older than I am. And he was the oldest people in the solid-state physics community. For our foreign colleagues, this is essentially the whole solid-state physics community in 1969, only 51 years ago. Here is Sergio Mascarenhas, and this is myself. I had returned from my PhD just 1 year earlier. But then I was convinced by a few colleagues, Sid, Rios, Fittipaldi, Maurício, and Marco, and Sergio Mascarenhas, to come from Rio to Recife. And that was a great move. I never thought that that was the most important decision in my life. Sergio Mascarenhas told me at that time that I had a golden opportunity in my life. And I thought he was kidding, because I was in Rio de Janeiro. And he said, this is the golden opportunity of your life to go to Recife. I thought he was kidding, but he was not kidding. He is a person with farsight. And then I came to Recife. 1 year and a half later, we received the first equipment. And here, então, Sid, that is the chair of this section here, Maurício, and Fittipaldi, that left and never returned for some reason. When Mascarenhas visited us in 1978, we had a celebration. He gave a talk, and here are colleagues at that time. Now, again, Mauricio, Sid, Fittipaldi, Mascarenhas, and then Fernando, who just spoke. Fernando was an undergraduate student at that time. Several other important colleagues, I don't have the time to mention their names. And then I started looking at photos with all of you. And I found these photos playing soccer, football, with Pavão here, Eduardo Fontana, and Mauricio here. Fontana, this is the only photo of ourselves that I could find. I'm here. This picture actually was inverted. I played in the right wing, not left wing. And then I'm going to mention a few encounters that we had. In the most important meetings that we had. All of the foreign participants here today have had an important role in ICM, in IUPAP. Berger is the current president of the Magnetism Commission, C9. Fernando is a member of C9. He is Múcio Continentino, who was a member previously, and he is Mauricio. And this was ICM in Paris in 1988. The first ICM I actually participated was in Boston when I was a student. And this was back in 1967. I also went to Amsterdam in 1976. And from then on, I went to most of ICMs. In 1997, I don't have any photo with you, but I had a photo with my important supporter, Adela. She went to all ICMs with me after some time. So here's a photo with Adela. Adela also helped in preparing this workshop, giving inside information to Fernando. And then we had ICM 2000 in Recife. I tried to find some of you here, but it was impossible. This was the opening day, registration day. We had the carnival, and these are toys from Olinda. Then we had a good time with good music. And then we had the conference. And I found some friends in some photos. He is Peter Grimmel, he is Albert Fer, and he is Mario Babish. Mario Babish is a Brazilian who was a co-author of the first paper on the giant magneto resistance. Here's another photo, and I could find Burker Hillebrands. He had dark hair and dark beard at that time. This is Flavio Aguiar, one of the organizers of this workshop. I thank you all. I thank you, Flavio. I thank you, Burker, for your participation. And then in the closing session of ICM 2000, we had Dino Fiorani, because usually, always, the chairman of the following ICM participates in the closing ceremony, and there's a formal transfer of responsibility. So I was here, and I transferred the responsibility for Dino Fiorani, and he was the chairman of ICM 2003 in Rome. I couldn't find pictures of any of you taken in the ICM at Rome. And then we jumped some time, and as you remember, 2005 was the International Year of Physics. And the closing of the International Year of Physics was done officially in Recife. The opening was in Paris, at UNESCO headquarters. But the closing was here. And then we had, brought by José Rios, we had Claude Coelho, who was already a Nobel Prize winner, and Sergio Rezende, who won the Nobel Prize a few years later. He is Ivo Fittipaldi. I thank you, Fittipaldi and Rios, for your presence here today. And then in 2013, our university gave a title of Doctor Honoris Causa to Sergio Mascarenhas. Here is Sergio Mascarenhas again. And then we had a meeting with the founders of the department. And I thank you again, Fittipaldi, City, Mauricio, Rios, and Mascarenhas for your participation in this celebration tonight. And then the only photo that I could find with Manuel was the same photo that he showed before. If you look carefully in my photo, you see that we are wet. He's more wet than I was because we were walking along the reef, and then a big wave came and we got wet. But we were happy, no problem getting wet when the temperature is 26, 27. And this is the downtown Recife on the background. Here we were walking through a reef, which is has a very nice sculpture and very nice place. Manuel, this place today has been completely remodeled. All of these are a new department store, restaurants, and so on. The whole downtown Recife was remodeled, and it's a very nice place to go today. Emmanuel was the organizer of the ICM 2 years later in Barcelona. And I went there, and that's the only photo that I have from the conference. My own photo. I put my camera on the automatic, and I took my own photo. And then we go to 2016, and I went to Spetses for a workshop called Spin Orbit Coupling and Topology in Low Dimensional Systems, organized by Albert Fert and Aranopoulos, a great person. Spetses is an island in Greece. And I was invited because we had done some work with graphene. And here's a photo of not everybody, because this was taken the last day. Some people have left. And here's Axel Hoffman and Albert Fert. And we had great fun. In many respects, great fun with physics and great fun in being in an island that the sea around the Spetses is like a Caribbean sea. So I have another photo of Axel Hoffman swimming in this Caribbean like very nice sea. I didn't do the same because I didn't think we would do it, and I didn't have my swimming suit. Axel Hoffman, again, just 1 year later, he came to Natal. In Natal, there is an International Institute of Physics, very nice place. And there was Axel Hoffman and Carl Chesma, who spoke to us today. Chesma is a full professor at the University of Natal. Also here we see Garrett Bauer and Jarod Serkovignac and other colleagues. And then, again, another ICM 2000 in San Francisco. There was Burker, as I said, he's the president of the Magnetism Committee, so he has the role of conducting part of the meeting. And here's Burker giving the prize to 4 young scientists that were chosen in that conference. Here it is. Nissim, I couldn't find any photo with her. I know we have taken photos together, but I couldn't find. So I show some papers about which you already talked in the detail. I want to thank you for the cooperation that we had 50 years ago. For me, it was very nice meeting you because when I went to the university in Rio, there was no laboratory. I was an experimentalist, but I had had a theoretical supervisor, and I could do some calculations. But the interaction with the Sinzaguri was very important for me in my first years of activity in Brazil. I learned many things from you, Nissim. Thank you for what I learned from you, and thank you for your participation today. Belita, again, you showed a photo with me, but I don't have that photo. I could not find a single photo with you. So what I have to do is to show a photo of a paper that we wrote. We also had a very interesting interaction for a few years, and we published this interesting paper on dynamics response of local maggots. And my thanks again to my colleagues, Roberto, who spoke today, and thank you, Roberto, for the very profitable interaction we have had. Fernando Machado, thank you for our interaction overall this year, and thank you for your role in organizing this workshop. Antonio Azevedo, thank you for your friendship, your companionship in the lab, and for your role in this workshop. And Eduardo Padrón was not in the photo because he was working in the lab. So Eduardo, thank you also for your participation in this workshop. And last but not least, I thank my family. So here I have my brother, one sister, another sister, and another sister. We are five. We had a brother who died several years ago. My daughters, Isabel, Marta, and Claudia, and my wife, Adela. Thank you all, and thank you all for your participation in the workshop. I'm really thankful, and I'm really touched with all of this. Thank you very much.
I think that I should say the last words in this symposium. I would like to say thank you for everybody who participated in this symposium, and I hope that for several more years we'll have the opportunity to celebrate the anniversary of Sergio again. So thank you very much.
Before we have to celebrate your anniversary, dinners.
I am much more. Okay, so thank you very much for your contribution to this symposium. Goodbye, everybody.
Best wishes, Sergio.
Sérgio.
Tanti auguri.
Sérgio, parabéns. Sérgio, eu mandei aqui uma mensagem para você no chat, para você mandar foto para mim, para os meus e-mails. Aquela foto do futebol. Manda para mim que eu não tenho aquela foto.
Vamos lá, eu não sei se eu tenho o seu e-mail.
Eu botei aqui no chat, está aqui no chat, aqui no diálogo. Certo? Valeu.
Ok.
Tchau.
Entrou a Adélia. Ela estava assistindo.
See you soon.
See you soon.
Goodbye.
Tchau.
Tchau, tchau. Parabéns.
Parabéns.
Very nice celebration. Bye-bye.
Yeah. Bye.
Bye.